Welcome. Find a comfortable place to rest. Let your body settle, let your breath slow, and allow the world outside to grow quiet. You're safe here. You're still. And tonight, we are going to travel somewhere extraordinary. We're going back further than history, back further than memory, back to a time when the Earth itself was young, when the sky burned with possibility, and when life was only just beginning to discover what it could become. Tonight, we follow the dinosaurs, from the very first moment life stirred on this ancient Earth, to the final, quiet day when the great age of giants came to an end. This is not a story of monsters. This is a story of survival, of beauty, of a world so different from our own that it almost seems like a dream. So close your eyes if you like, breathe gently, and let the Earth carry you back across the ages. We want to thank you for supporting us, and it would mean so much if you could support the channel by leaving a like and subscribing to help us keep this channel going. If you enjoy listening to sleepy prehistoric stories like this, subscribe. I post stories like this weekly. Anyways, back to the video. To understand the dinosaurs, we must first understand the world they inherited, and that world was not handed to them easily. It was earned through hundreds of millions of years of slow, patient, extraordinary transformation. Imagine the Earth as it existed long before any creature walked upon dry land. The oceans are warm and shallow in places, deep and cold in others. The skies are pale, hazy blue, the atmosphere still thickening with oxygen produced by tiny photosynthetic organisms too small to see with the naked eye. There are no trees yet, no grass, no flowers. The continents are bare and rocky, swept by winds that carry nothing but dust and the faint chemical traces of ancient volcanoes. Life exists, but it exists quietly. In the oceans, strange creatures drift and crawl through warm water. Soft-bodied jellyfish pulse gently through the dark. Trilobites, those elegant armoured animals, pick their way along sandy seafloors that have not yet been named. Enormous sea scorpions move with a slow, deliberate grace through shallow tidal zones. And below all of this, in the sediment itself, in the cracks between rocks, in the thin film of moisture that coats every stone, microbes carry out the ancient work of life, breaking down minerals, releasing gases, preparing the ground in their own invisible way for everything that is to come. This is the Cambrian period, and then the Ordovician, and then the Silurian, each age flowing into the next like water through open hands. The Earth is changing. The continents shift slowly, driven by forces deep within the mantle, by the slow convection of rock so hot it moves like thick honey over millions of years. Land masses that were once joined begin to drift apart. Others collide, throwing up mountain ranges that will erode back to plains before any creature with eyes can see them. The first plants begin to colonize the land during the Silurian, around 440 million years ago. They are small at first, mossy, low-growing things that cling to the edges of rivers and lakes where moisture is constant. But over millions of years they grow taller, their roots dig deeper, their stems grow woody and strong, and by the time we reach the Devonian period, something remarkable has happened. Forests exist. Not dense, lush forests like the ones we know today, but forests nonetheless. Strange primitive trees with no leaves, their bare green trunks reaching toward a sun that seems just a little brighter than it did before, because the atmosphere is finally rich enough in oxygen to carry light the way it does today. With the plants come the insects, small at first, but growing over millions of years into creatures of astonishing variety. The first amphibians pull themselves out of the water and take their first tentative steps on land. These are not graceful creatures. They are heavy and slow, still dependent on water for reproduction, still needing to return to rivers and swamps to lay their eggs. But they are a beginning, a foothold, life's first serious claim on the dry world. And then comes the Permian, a long, slow age of sprawling forests and strange creatures. Mammal-like reptiles called synapsids dominate the land. Some of them are enormous, with elaborate sail-like structures on their backs that absorb heat from the morning sun. Others are small and quick, darting between the legs of their larger relatives in search of insects and seeds. The world feels almost familiar in some ways. There are ecosystems here, food chains, predators and prey. The same fundamental dance that life has always performed, but played out on a stage that looks nothing like the world we know. But the Permian does not last. Nothing lasts forever, not even ages that stretch across tens of millions of years. Around 252 million years ago, something happens deep beneath what will one day be called Siberia. A vast region of the Earth's crust, weakened by the slow movements of the mantle below, begins to fracture. Magma surges upward through the cracks. Not in a single dramatic explosion, but in a series of eruptions that continue for hundreds of thousands of years. Lava flows across a landscape as large as the continental United States. Volcanic gases billow into the atmosphere in quantities so enormous they change the chemistry of the air itself. Carbon dioxide levels spike, the oceans warm, the chemistry of the seas shifts, becoming more acidic, hostile to the calcium carbonate shells that so many marine creatures depend on. Oxygen levels in the deep ocean plummet, and on land, the slow warming brings drought, wildfires, the collapse of the great forests that had covered the continents for millions of years. This is the Great Dying, the Permian Triassic extinction event, the largest mass extinction in the history of complex life on Earth. More than 90% of all marine species vanish. More than 70% of all land vertebrate species disappear. Entire lineages that had survived for hundreds of millions of years simply cease to exist. The world is not destroyed, but it is emptied, quieted in a way it has not been since before the Cambrian explosion first filled the oceans with animal life. What remains is a scattered, fragile collection of survivors, creatures that happened to be in the right place, or had the right biology, or simply got lucky in the random, brutal lottery of extinction. Among them are small reptiles, ancestors of the lineages that will one day give rise to the dinosaurs. They are not yet recognizable as anything special. They are simply alive, surviving in a world that has been wiped almost clean, a world now ready to be filled again. The recovery after the Great Dying is slow. For millions of years, the Earth feels strange and sparse. Ecosystems are simple, dominated by a few opportunistic species that spread quickly into the emptied ecological niches. The seas begin to fill again, slowly, cautiously, as if life itself is not quite sure the danger has passed. But by about 247 million years ago, the world has changed enough that something new becomes possible. The Triassic period has begun. The scattered land masses of the Earth are still mostly joined together in one enormous supercontinent called Pangaea, a single vast landmass that stretches almost from pole to pole. Its interior is dry and hot, swept by monsoon winds that bring intense seasonal rains to the coasts, but leave the deep interior parched and red. The equatorial regions bake under a sun that seems to bear down harder without the moderating influence of distant oceans. It is in this world, this dry, red, sun-scorched world still recovering from the greatest catastrophe it has ever known, that the first dinosaurs appear. They are not yet the giants. They are not yet the masters of the Earth. They are small, quick creatures, two-legged in many cases, no larger than a medium-sized dog. They move with an energy and precision that sets them apart from the other reptiles of their time. Their legs are positioned directly beneath their bodies, not splayed out to the sides the way a lizard holds itself. This gives them a more upright stance, a more efficient gait, the ability to move quickly and sustain that movement in a way that their sprawling limbed relatives cannot. We do not know exactly when the first true dinosaur appeared. The fossil record is incomplete, as it always is, gaps filled in slowly by the patient work of paleontologists who spend their careers on their hands and knees in remote deserts and canyon walls, brushing dust from bones older than imagination. But by around 230 million years ago, in the Late Triassic, creatures that we would recognize as dinosaurs are present in the fossil record. Creatures like Eoraptor, a small bipedal predator from what is now Argentina, barely a meter long, light-boned and sharp-eyed and fast. Creatures like Herrerasaurus, larger, more powerful, already showing the elongated body and powerful hind limbs that will characterize the predatory dinosaurs for the next 165 million years. They are not alone in this world. The Triassic is full of other reptiles, many of them larger and seemingly more dominant than these early dinosaurs. The etosaurs are armored, pig-like herbivores that graze across the floodplains in large herds. The phytosaurs look remarkably like crocodilians, long-snouted and semi-aquatic, patrolling the rivers and lake margins. Rauisuchians are large, powerful predators with an upright stance of their own, some of them reaching lengths of 5 or 6 meters, the dominant hunters of their time. Compared to these animals, the early dinosaurs seem almost unremarkable. Small, peripheral, present, but not yet important. And yet, something about them is different. Something about the way they are built, the way they grow, the way they move and hunt and reproduce, gives them an edge that is not yet obvious but will become impossible to ignore. The night is quiet in the Triassic. The air is warm and thick with moisture near the rivers, dry and dusty away from them. The sounds are unfamiliar. No birds call from the trees because there are no birds yet, and the trees themselves are different. Conifers dominate, along with cycads and ferns and horsetails that grow in dense stands along the water's edge. Small reptiles rustle through the undergrowth. Insects buzz and whir in the warm air. And somewhere in the darkness, a small, quick shape moves through the ferns, hunting something smaller, driven by the same hunger that drives all living things across all of time. It is not yet the age of dinosaurs, not quite, but it is coming. Slowly, surely, in the patient way that great changes always come, it is coming. The Triassic world is beautiful in its strangeness. The sky at dusk would look different to us. The stars would be the same, but the air itself would carry a different quality of light, filtered through an atmosphere with a slightly different chemical composition. The sunsets over the red sand interior of Pangaea would be long and gradual, the light changing from orange to deep red to purple as the sun dropped below a horizon, unbroken by mountains in the interior plains. And in those long, quiet twilights, the early dinosaurs would emerge from wherever they had sheltered during the heat of the day, moving across the cooling sand with their quick, efficient stride, the world spread out before them like a promise not yet fulfilled. Breathe gently now. Let the image settle. The red sand, the warm air, the first small shapes of what will become the greatest dynasty of land animals the world has ever seen. They do not know what they will become. They simply live, as all creatures simply live, one breath at a time, one heartbeat at a time, in the only world they have ever known. The seas of the Permian were among the richest marine environments the world had ever seen. Coral reefs of astonishing complexity spread across the shallow tropical shelves, their branching and massive forms providing habitat for hundreds of species of fish, mollusks, echinoderms, and countless invertebrates whose names we would not recognize because nothing remotely like them exists today. Fusulinids, those tiny wheat-grain-shaped foraminifera, accumulated in such vast numbers that their shells formed thick layers of limestone across wide areas of the ancient seabed. Brachiopods, superficially similar to clams but evolutionarily very different, lay in dense beds on the seafloor, filtering nutrients from the slow currents. The Permian land was dominated by the therapsids, those mammal-like reptiles that have a special claim on our attention because we are, in the most literal evolutionary sense, their descendants. The most advanced therapsids of the late Permian, the cynodonts, were already experimenting with features that we associate with mammals. Their teeth were becoming differentiated, not all the same peg-like shape but varying in function from front to back, incisors for grasping, canines for stabbing, complex cheek teeth for processing food. Their skulls were changing shape in ways that suggest their brains were expanding, and their posture and locomotion were becoming more upright, more mammalian. Some cynodonts may have had whiskers, those sensory hairs that modern mammals use to navigate in the dark. Some may have been at least partially endothermic, generating their own body heat metabolically, rather than relying entirely on the sun. They were moving, in other words, in the direction of warm-bloodedness, of the intense, self-sustaining metabolism that makes mammals such effective colonizers of every environment on Earth. And then the Great Dying took almost everything. The cynodonts were nearly eliminated. A few lineages survived, reduced to small nocturnal forms clinging to existence in whatever refuges the devastated world provided. They would go on, eventually, to give rise to the true mammals. But that story is for another night. Tonight we follow a different lineage, one that emerged from the same catastrophe to take a very different path. The archosaurs, the lineage that would eventually produce both the crocodilians and the dinosaurs, were present in the Permian but were not yet dominant. They were among the survivors of the Great Dying, and in the Triassic they diversified rapidly into the ecological space left empty by the extinction. Early archosaurs show a remarkable diversity of body plans, experimenting with different locomotion strategies, different diets, different sizes. The evolutionary space was wide open, and they were exploring it in every direction. One of the most important evolutionary innovations that appeared in the archosaur lineage in the Triassic was the erect parasagittal posture, the positioning of the limbs directly beneath the body rather than splayed to the sides. Modern crocodilians can actually walk in both a sprawling posture and a more erect, galloping gait, giving us a living demonstration of what the transitional forms might have looked like. But the fully erect posture of the dinosaur lineage, with legs positioned directly beneath the body in the same plane as the spine, was a profound advantage in terms of locomotion efficiency. An animal with a sprawling posture must use considerable muscular effort to support its body weight against gravity with every step. An animal with an erect posture has its limbs acting more like columns, transmitting the body weight directly to the ground with less muscular effort. This means more energy is available for locomotion, for growth, for reproduction. It is one of the reasons that the erect-postured dinosaurs could grow so much larger than their sprawling-limbed competitors. The bigger the animal, the more important this efficiency becomes. The Triassic recovery was not just a story of dinosaurs filling empty niches. It was a story of multiple lineages competing, experimenting, failing and succeeding in a world still finding its new ecological balance. The dinosaurs did not win the Triassic. They simply survived it well enough to be in a good position when the end-Triassic extinction cleared the field again. The deep history of the dinosaurs, stretching back through the archosaurs to the earliest Triassic survivors of the Great Dying, is a story of resilience and opportunity, of lineages that persisted through catastrophe and then expanded into the space that catastrophe created. It is a story that will be told again at the end of the Cretaceous, when the birds carry the dinosaur legacy forward through another catastrophe, another clearing, another expansion into empty space. Life is very good at surviving. Life is very good at finding the crack in the rock, the gap in the forest, the moment of vulnerability in the competition that allows a new approach, a new body plan, a new way of being alive. The dinosaurs found their moment in the Triassic. They held it for 165 million years, and their descendants are holding it still. The Triassic night settles over the recovering world. The stars are bright above the dry red lowlands of the supercontinent. Small archosaur relatives move through the darkness, hunting insects, avoiding the larger predators, living their small and circumscribed lives with the intensity that all small lives share. Among them, too small to distinguish as anything special, the ancestors of the dinosaurs are doing what they have always done, surviving, adapting, preparing, without knowing it, for the extraordinary future that is coming. The world is approximately 220 million years old by the time we reach the Middle Triassic, and it is still healing, still finding its new rhythms after the catastrophe that emptied it. The supercontinent of Pangaea stretches across nearly the entire globe, and in its vast interior the climate is extreme. Scorching summers, dry winters, great seasonal floods that sweep down from the highlands and spread across the lowlands in shallow, muddy sheets before the dry season drinks them back up again. But life is resilient. Life, once it has found a foothold, does not easily surrender it. The dinosaurs of the early to mid-Triassic are still a minor part of this world. They share it with a rich community of other reptiles, with insects, with early amphibians, with the mammal-like reptiles called therapsids that are slowly, quietly, in their own separate evolutionary experiment, beginning to move toward the body plan that will one day produce the mammals and eventually ourselves. The world feels busy in a particular way, full of small dramas playing out at the level of individual creatures, each one navigating its own daily challenges of finding food, avoiding predators, finding shelter from the heat. Picture a broad, dry flood plain in what will one day become the American Southwest. The rocks that will preserve the fossils of this moment are called the Chinle Formation, and they are beautiful rocks, banded in reds and purples and pale lavenders, painted by the slow chemical processes of burial and time. In this place, in this time, the land is dotted with patches of forest near the rivers. Tall, ancient conifers rise above the smaller cycads and tree ferns. Fallen logs lie across the ground, their interiors being slowly consumed by fungi their surfaces crawling with millipedes and early beetles. A creature moves through the undergrowth here. It is Coelophysis, one of the earliest dinosaurs we know well, preserved in extraordinary numbers in a famous bone bed in New Mexico. It is a small animal, barely 2 meters long, but slender and light, built like a living arrow. Its bones are hollow, reducing its weight while maintaining structural strength. Its legs are long and powerful relative to its body. Its neck is flexible, its head narrow and sharp, equipped with small recurved teeth perfect for snatching at lizards and insects and small proto-mammals. It moves in the early morning before the heat of the day sets in. Its movements are quick and jerky, like a bird, full of sudden pauses and sharp turns of the head as it monitors its surroundings. It is both predator and potential prey here, quick enough to catch the small animals it hunts, but not yet large enough to be beyond danger from the larger Rossukians that also inhabit this landscape. Watch it. Pause at the edge of a clearing. Its head tilts to one side, one large eye catching the movement of something small in the grass. For a moment it is perfectly still, every muscle coiled, its breath held. And then it strikes. A blur of movement, and something small and fast disappears into its narrow jaws. It raises its head, swallows, and moves on. This is life at the beginning of the dinosaur age, not spectacular yet, not the thundering giants of later ages, just small, sharp, efficient creatures doing what they have always done, what all animals have always done, finding enough food to survive another day. But something is about to change. Something is always about to change in the patient geological story of the Earth. Around 201 million years ago, as the Triassic draws toward its close, another catastrophe unfolds, not as severe as the Great Dying, but devastating enough. The supercontinent of Pangaea has been rifting along its central axis for millions of years, the crust stretching and thinning as the landmass slowly begins to break apart. And now, along the zone that will one day be the Atlantic Ocean, vast quantities of magma once again push up through the weakened crust. Another enormous flood basalt eruption begins. The Central Atlantic Magmatic Province, one of the largest volcanic events in the last 500 million years. The effects ripple outward. Gases change the atmosphere. Temperatures spike. The large dominant reptiles of the Triassic begin to disappear. The phytosaurs vanish. The etosaurs vanish. The Rauisuchians vanish. Many of the crocodilian relatives that had been so successful in the Triassic disappear. And the dinosaurs survive. We do not know exactly why. Perhaps it is their more efficient metabolism. Perhaps it is their upright posture and more active lifestyle. Perhaps it is something about their reproduction, their ability to lay eggs in a wider variety of environments. Perhaps it is simply the accident of geography, that the populations that happened to survive were dinosaur populations, while the populations that happened to perish were other reptiles. Whatever the reason, when the Triassic-Jurassic extinction event fades and the world begins the slow work of recovery, the dinosaurs emerge on the other side of it as the dominant large land animals on Earth. The competition has been cleared away. The ecological niches that the other great reptiles of the Triassic filled are now empty, and into that emptiness the dinosaurs begin to expand. This is one of the great moments in the history of life, a turning point subtle in its first expression, monumental in its consequences. The dinosaurs do not suddenly appear as giants. The transformation is slow, measured in millions of years, but the trajectory is unmistakable. By the early Jurassic, around 190 million years ago, dinosaurs are already more diverse than they have ever been. The basic body plans that will define the group for the next 160 million years are already established. There are the theropods, the primarily bipedal carnivores, ranging in size from small, quick hunters to the ancestors of increasingly enormous predators. There are the sauropodomorphs, the long-necked plant-eaters, already experimenting with the elongated necks and large-barreled bodies that will eventually produce the largest land animals in Earth's history. And there are the ornithischians, a diverse group of plant-eaters that will give rise to some of the most spectacular animals the world has ever seen. The Jurassic world is greener than the Triassic. The rifting apart of Pangaea has changed the climate. The interior of the continent is still dry in places, but the coasts and the regions between the separating land masses are warm and humid, filled with lush vegetation. Forests of conifers and cycads and ferns stretch across the landscape. The air is thick and warm. Rivers run full through broad valleys. It is in this world that the dinosaurs begin their great expansion, and as we follow them into the Jurassic, we move from the prologue of their story into its first great chapter. The world they are about to create is one of the most spectacular that has ever existed on this planet. Let yourself rest into the imagery. The warm Jurassic sky, the smell of ferns and wet earth, the distant sound of something very large moving through the trees. You are safe and still, and the story is just beginning. The early Jurassic herbivores are already impressive by the standards of modern animals, but they are small by comparison to what is coming. Massospondylus, a sauropodomorph from South Africa and Zimbabwe, reaches about 5 meters in length. It walks on its hind legs much of the time, using its long neck to reach vegetation others cannot access. Its body is lean and elongated, its tail long and counterbalancing, its feet equipped with large thumb claws that may have helped it tear branches from trees. It is a gentle-looking animal in some ways, moving carefully through the forest understory, pausing to pull mouthfuls of cycad fronds, chewing slowly as it moves on. But watch the forest around it carefully, because the forest is not entirely safe. Dilophosaurus, a large theropod of the early Jurassic, is already a formidable predator. 6 meters long, it moves with the confidence of an animal near the top of its local food chain. Its most distinctive feature, the paired bony crests that run along the top of its skull, may be display structures used to attract mates or intimidate rivals, or they may play some other role we have not yet determined. Whatever their function, they give Dilophosaurus a striking appearance, elegant and slightly alien, a reminder that real animals are often stranger and more beautiful than our imaginations would create. It moves through the early Jurassic forest with the careful, deliberate precision of a large predator that does not need to rush. When it hunts with patience, waiting for the right moment, the right angle, the vulnerability in its prey that signals the opportunity to act. There is no cruelty in this. There is only biology, the ancient necessary dance of energy moving from one form to another, the fundamental process that has driven evolution since the first living molecule began to replicate. The Jurassic deepens, time flows in its patient, invisible way, and the dinosaurs grow. The end Triassic extinction was not a single event in the way the Chicxulub impact was. It was a prolonged period of environmental stress, spanning perhaps 1 million years or more, during which conditions deteriorated slowly and then more rapidly, before finally beginning to recover. For the animals living through it, it would have felt not like a single catastrophe, but like a world that was simply becoming steadily less hospitable, less productive, less reliable. The great flood basalt eruptions of the Central Atlantic magmatic province produced something called a carbon dioxide spike, a rapid increase in atmospheric carbon dioxide concentrations that drove global temperatures upward. Warmer temperatures meant different patterns of rainfall and drought. Vegetation zones shifted. Ecosystems that had been stable for millions of years were disrupted as the plants that had always been there began to die back and be replaced by different species better suited to the new conditions. For the large, specialized reptiles of the Late Triassic, this gradual deterioration was lethal. The etosaurs, feeding on specific vegetation in specific habitats, found their food sources failing. The phytosaurs, dependent on productive aquatic ecosystems that were being disrupted by the changing hydrology of the deteriorating landscape, dwindled. The Rauisuchians, as apex predators, were among the last to feel the effects but also among the least able to adapt when the prey populations that supported them collapsed. The dinosaurs, by contrast, seem to have been more generalist in their ecology, more flexible in their diets and habitats. The small, fast-moving early dinosaurs were capable of eating a wide variety of things: insects, small vertebrates, seeds, vegetation, whatever was available. This dietary flexibility gave them a resilience that their more specialized contemporaries lacked. There is a lesson in this that echoes down the geological ages. The specialists, the perfectly adapted, the animals that have optimized so completely for a particular way of life that they cannot function outside it, these are the first casualties of catastrophe. The generalists, the flexible, the animals that can make do with less than ideal conditions, these are the survivors. The dinosaurs of the Triassic were, in their early days, supreme generalists, and that flexibility was what carried them through. By the earliest Jurassic, approximately 200 million years ago, the world had changed enough that the dinosaurs' position in it had changed dramatically. They were no longer a minor component of a diverse archosaur fauna. They were the dominant large land vertebrates, the only group with representatives at every level of the terrestrial food chain. The herbivore niches, the predator niches, the large, the medium, and the small, all were being filled by dinosaurs, or were in the process of being filled. The speed of this ecological takeover is one of the most striking things about the Triassic-Jurassic transition. In geological terms, it was almost instantaneous. Within a few million years of the end Triassic extinction, dinosaurs had diversified to fill ecological roles that had been occupied by very different animals just a few million years before. This suggests that the diversification was not driven primarily by new evolutionary innovations within the dinosaur lineage, but by the release from competition that the extinction provided. The ecological space was there, and the dinosaurs expanded into it as fast as their evolutionary capacity allowed. The early Jurassic sauropodomorphs, the ancestors of the great long-necked sauropods, were already experimenting with large size. Animals like Volcanodon from Zimbabwe or the slightly later Shunnosaurus from China were already developing the characteristic sauropod body plan: long necks, relatively long tails, 4 legs for support, a large barrel body for processing enormous quantities of plant material. They were not yet the giants of the late Jurassic, but the trajectory was established. The prosauropods, an earlier grade of sauropodomorph, had been present since the late Triassic. Animals like Plateosaurus from Germany and Switzerland could rear up on their hind legs to reach vegetation in a way that their fully quadrupedal descendants could not. They were medium-sized animals, perhaps 6 to 8 meters long, moving through the late Triassic and early Jurassic forests on a combination of 4 legs and 2, browsing on whatever vegetation was at hand. In parts of Europe, the late Triassic fossil beds contain literally thousands of Plateosaurus individuals, evidence of an animal that was extraordinarily successful in its time and place. But the prosauropods were also a transitional form, not quite the specialized ground-level browsers that the later hadrosaurs would be, not quite the high canopy browsers that the tall-necked sauropods would become. They occupied a middle ground that was productive in the Triassic and early Jurassic, but that would eventually be displaced as their descendants moved in different directions and became better at being what they were trying to be. This is how evolution often works. Not through sudden revolutionary change, but through gradual optimization, each generation nudging slightly closer to a more efficient version of the same basic approach, until after millions of generations the accumulated nudges have produced something so different from the starting point that the connection between them is visible only in the fossil record. The Jurassic begins its long, warm, stable tenure. The world will not see another mass extinction for the remainder of the Mesozoic. 145 million years of relative stability lie ahead. 145 million years in which the dinosaurs can experiment, diversify, grow larger, grow more complex, fill every available niche, and then subdivide those niches and fill the subdivisions in turn. It is the golden age of the dinosaurs, and it is just beginning. Let the early Jurassic settle around you, the warm, humid air, the forests of conifers and cycads and tree ferns, the distant sound of large animals moving through the vegetation, the sky a pale blue above the canopy, a few clouds building in the heat of the afternoon, everything new, everything possible, everything just beginning. To fully understand where the dinosaurs came from, we need to spend more time in the Triassic, that strange, transitional, underappreciated world that bridged the catastrophe of the Permian extinction and the lush abundance of the Jurassic. The Triassic is often treated as a prologue, a waiting room before the real story begins, but it was a world complete in itself, rich with its own dramas and its own extraordinary life. The early Triassic, the period immediately following the Great Dying, was in many ways the strangest world that has existed in the history of complex life. With 90% of marine species and 70% of terrestrial vertebrate species gone, the survivors inhabited an emptied landscape that must have felt, to any consciousness capable of perceiving it, like the end of things. And yet those survivors were already, in the quiet and invisible way of evolution, the beginning of everything that came after. The recovery was uneven and geographically complex. Some regions recovered faster than others. Coastal marine environments fed by nutrients washing down from the land and warmed by shallow water recovered more quickly than the open ocean. Tropical land environments, with their year-round warmth and moisture, recovered faster than the harsh seasonal interiors of the supercontinent. The survivors were not distributed randomly across the landscape. They were clustered in refuges, the places where conditions had remained most tolerable through the catastrophe, where enough food and enough moisture and enough of the right temperature range had persisted to allow life to continue. From these refuges, over the millions of years of the early to mid-Triassic, life spread outward. Species expanded their ranges as conditions improved. New species evolved from the survivors as the empty ecological niches presented selection pressures that had not existed before. The world was, in a very real sense, being rebuilt from scratch, and the builders were the organisms that had been lucky enough, resilient enough, or simply positioned well enough to survive. The archosaurs, the group that would eventually give rise to the dinosaurs, the crocodilians, and the pterosaurs, were among the most successful of the early Triassic colonizers. They seem to have had a particular advantage in the dry, hot conditions of the early Triassic supercontinent interior. Perhaps it was something about their physiology, a more efficient water conservation system. Perhaps it was their feeding ecology, a greater dietary flexibility that allowed them to exploit whatever was available in the reduced recovering world. Whatever the reason, they diversified rapidly through the Triassic and came to dominate many terrestrial environments by the middle of the period. The plant life of the early Triassic was dominated by leucopsids, ferns, and horsetails, the same groups that had been the primary colonizers after earlier disturbances. The more complex vegetation of the late Permian had been largely eliminated, and its reconstruction took time. By the mid-Triassic, conifers were expanding rapidly, taking advantage of the drier conditions of the supercontinent interior. The Triassic forests were different from what had come before, simpler in structure, less diverse in composition, but increasingly productive as time went on and conditions improved. It is in these recovering mid-Triassic forests that we should look for the earliest true dinosaurs. Or rather, the earliest true dinosaurs are looking for us, with sharp eyes tuned to the detection of movement and the assessment of opportunity, because that is what a small theropod does. It watches, it waits, it acts when the moment is right. Eoraptor, from the Ischigualasto Formation of Argentina, approximately 230 million years old, is one of the earliest dinosaurs we know. It is a small animal, barely a metre long, weighing perhaps 5 to 10 kilograms. Its skull is lightly built, its jaws equipped with both the leaf-shaped teeth of an herbivore and the more blade-like teeth of a carnivore, suggesting it was an omnivore capable of eating both plant material and small animals. Its hind limbs are long relative to its body, its stance fully erect in the dinosaurian fashion. Looking at Eoraptor, we see an animal that does not yet look like anything famous. It does not look like Tyrannosaurus. It does not look like Triceratops. It looks like what it is, a small generalist early archosaur experimenting with a body plan that will, given time, produce the most spectacular array of land animals the world has ever seen. The Ischigualasto Formation of Argentina, along with the roughly contemporary Santa Maria Formation of Brazil, preserves the earliest chapters of the dinosaur story in remarkable detail. These South American formations were deposited during the late Triassic, when the southern part of Pangaea was drifting slowly, but was still continuous with the north, allowing animals to disperse across enormous distances over geological time. The early dinosaurs that evolved in the South American segment of Pangaea were not isolated there for long. Their descendants spread northward and eventually colonized the entire supercontinent. What made the South American late Triassic a particularly productive birthplace for new lineages? The question is interesting. The region may have had a particular combination of habitat types and climate conditions that promoted evolutionary experimentation. The presence of large rivers and associated floodplains, alternating with drier upland environments, would have created a mosaic of habitats that selected for ecological flexibility, exactly the kind of flexibility that characterizes the earliest dinosaurs. The other great early dinosaur localities, the Chinle Formation of North America and the equivalent deposits of Europe and Africa, all tell similar stories of small, fast, ecologically flexible animals experimenting with the basic dinosaur body plan. None of them looks particularly special in retrospect. None of them, viewed in isolation, would lead you to predict what was coming. They are the beginning of a story whose ending will not be known for another 165 million years. The Middle Triassic world was a place of extraordinary evolutionary activity, not just in the dinosaur lineage but across the board. The pterosaurs, the flying reptiles, appeared in the Middle Triassic and took to the air with remarkable speed. Their origins are still somewhat mysterious. The earliest pterosaurs in the fossil record are already fully formed flyers, with the elongated fourth finger that supported the wing membrane already fully developed. We have not yet found the transitional forms that would tell us what the pterosaur ancestor looked like before it developed the ability to fly. The early pterosaurs were probably insectivores, using their elongated, toothed jaws to snap at large insects in midair. They were not large animals by the standards of the giants that would come later. Most early Triassic pterosaurs had wingspans of less than a meter, but they were extraordinary innovations, the first vertebrates to achieve true powered flight, more than 200 million years before the Wright brothers made a similar achievement in a very different kind of machine. The crocodilian lineage was also diversifying in the Triassic, producing forms that would surprise anyone who encountered them today. Early crocodilians were not the semi-aquatic ambush predators we know from modern rivers. They were terrestrial animals, some of them long-legged and fast-moving, cursorial predators that occupied the running predator niche in a way that the modern crocodilians, with their sprawling, low-slung posture, do not. The evolution of the modern crocodilian body plan, with its semi-aquatic lifestyle and ambush from water hunting strategy, came later in the Jurassic and Cretaceous. For much of the Triassic, then, the landscape was contested between multiple lineages of upright postured active archosaurs, all competing for the same ecological roles, all experimenting with slightly different approaches to the same fundamental challenges of life on a hot, dry, recovering Earth. The dinosaurs were one of those lineages. For most of the Triassic, they were not obviously the most successful. But they were persistent, and persistence in the long run is everything. The Triassic world, from its devastated beginning to its richly diverse close, was a world of recovery and reinvention, a world that demonstrated, if such demonstrations were needed, that life is not fragile, that the biosphere is not a delicate crystal that shatters easily and irreparably. It is more like a resilient network, a web that can be torn in many places and still hold together at its core, still rebuild from what remains, still produce, given time, the extraordinary complexity that catastrophe stripped away. This is not a reason for complacency about the current state of the world and the pressures that human activity is placing on the biosphere. A resilient system can still be pushed beyond the limits of its resilience, and the recovery from a mass extinction event takes millions of years. The world that emerges from recovery is never the same as the world that existed before. Species that were lost are lost permanently. Evolutionary lineages that were severed cannot be rejoined. The world moves on in a new direction from whatever survivors remain. But the resilience is real. The capacity for recovery is real. And knowing this, understanding the long history of catastrophe and recovery that is written in the rocks, gives us a perspective on the present that is both sobering and, in some ways, hopeful. Life has endured before. Life has rebuilt before. Life will continue in some form, whatever we do or fail to do. The question is, which form? Which life? How much of the extraordinary complexity and beauty of the current biosphere we carry forward into the future? That is the choice we are currently making day by day in the ordinary and extraordinary decisions of our collective existence. But these are thoughts for daylight hours. For now, let the Triassic settle its ancient dust over everything. Let the recovering world grow quiet in the evening warmth. Let the small, quick shapes of the first dinosaurs vanish into the ferns. The story continues. It always continues. One of the most surprising discoveries of modern paleontology is that the dinosaurs did not restrict themselves to the warm, tropical regions we typically associate with them. Dinosaur fossils have been found in deposits that were, at the time of their formation, within or very near the polar circles. These polar dinosaurs are a remarkable testament to the adaptability of the dinosaur body plan and to the extraordinary range of environments that these animals successfully colonized. The Cretaceous polar regions were very different from the modern poles. Without permanent ice caps, the climate was milder than today, and the midnight sun of the polar summer would have provided continuous growing conditions for vegetation for several months of the year. But the polar winter still brought months of darkness and cold, conditions very different from the subtropical warmth that most Cretaceous dinosaurs experienced. In Australia, which was positioned much further south in the Cretaceous than it is today, dinosaur fossils from the Otway and Strzelecki groups record animals that lived within the Antarctic Circle, roughly at the equivalent of modern southern tip latitudes, during the early Cretaceous. These animals lived through a polar winter in which temperatures may have dropped below freezing, and light was absent for months. The dinosaurs found there include a variety of ornithopods and theropods, suggesting established communities rather than occasional visitors. How did the polar dinosaurs cope with the long winter darkness? Several possibilities exist. Some may have migrated, moving northward toward warmer regions as the winter approached, a behavioral strategy similar to that of modern migratory birds. Some may have entered a form of dormancy, slowing their metabolism during the darkest months in a way comparable to the torpor of modern mammals or the brumation of modern reptiles. And some may simply have been active year-round, their warm-blooded metabolism allowing them to maintain activity in cold conditions, feeding on whatever was available during the winter months. The discovery of polar dinosaurs has important implications for our understanding of dinosaur physiology. A cold-blooded animal, dependent on external heat sources for its metabolism, could not survive the polar winter without extended dormancy. But a fully warm-blooded animal, generating its own heat internally, could potentially remain active even in sub-freezing conditions if it had sufficient food and insulation. The feathered, small theropods were almost certainly capable of this. Their bird-like physiology, including the insulating feathers that many of them possessed, would have allowed them to maintain body temperature even in cold conditions, just as modern birds remain active in Arctic winters. The larger dinosaurs present more of a mystery, since their enormous mass would have given them good thermal inertia, but their large surface area would have required substantial internal heat production to maintain. The evidence continues to accumulate that the dinosaurs were physiologically complex animals, not simply large lizards scaled up to improbable sizes. The rapid growth rates visible in the bone tissue, the maintenance of activity in polar environments, the evidence for bird-like respiratory systems with efficient air sac breathing, all of these point to animals with metabolism significantly faster and more active than those of modern ectothermic reptiles. The polar dinosaurs are, in a sense, an extreme test of the dinosaur model, and they passed that test. They lived where the conditions would have killed any ectotherm that could not hibernate, and they left fossils to prove it. They were there, in the dark and the cold of the polar winter, finding a way to survive in conditions that most of us associate only with the hardy fauna of the modern polar regions. The adaptability that this represents is extraordinary. It is the same adaptability that allowed the dinosaurs to colonize every habitable environment on Earth, from the equatorial tropics to the polar circles, from sea level to high-altitude plateaus, from dry desert interiors to wet coastal lowlands. It is the same adaptability that, in reduced form, allowed some of their descendants to survive the asteroid winter and carry the lineage forward to the present. The polar dinosaurs of the Cretaceous were a remarkable experiment at the edge of what the dinosaur body plan could achieve, and they succeeded. They were there, real and alive in the cold and the dark, breathing the frigid polar air, surviving in the place where the world was hardest. That too is the dinosaur story, the persistence, the reach, the refusal to be confined to the comfortable centre when there was still more world to inhabit. There is a quality to the Middle and Late Jurassic that feels almost mythological, a sense of scale, of abundance, of life at its most extravagant expression. We are now in the world that captures the imagination more than any other prehistoric age, the world of the giants, the world where the largest land animals in Earth's history first walked and fed and moved across a landscape so lush it seems almost impossible. The supercontinent of Pangaea has continued to break apart. The northern land masses, what will one day become North America, Europe and Asia, are still loosely connected but beginning to separate. The southern land masses, the future South America, Africa, Antarctica and Australia, are likewise drifting on their slow, inevitable courses. Between these separating continents, shallow seas have formed, warm and rich with marine life, providing new ecological niches and new climates as ocean currents shift and change. The climate of the late Jurassic is warm, warmer than today. There are no polar ice caps. The poles are cool and temperate rather than frozen. Forests extend much further north and south than they do in our own time. The tropics and subtropics are humid and lush, crossed by enormous river systems that carry silt and nutrients from the highlands to the great coastal plains where the largest dinosaurs congregate. And those coastal plains, those vast, flat, river-crossed lowlands, they are where the story of the Jurassic giants unfolds. Picture the Morrison Formation, the ancient sediments of the late Jurassic preserved across much of the western United States. When you walk through the badlands of Colorado or Wyoming or Utah today, and look at the banded layers of grey and red and purple rock, you're looking at the compressed and fossilized remains of a world that existed 150 million years ago. A world of enormous rivers flowing from highlands to the west across broad floodplains. A world of gallery forests lining the riverbanks and more open, drier habitats between them. A world that, during the wet season, would have been green and lush and full of the sounds of enormous animals moving through vegetation. It is here in this world that we meet the sauropods in their full glory. The sauropods are the long-necked, long-tailed, four-legged plant-eaters that have been evolving and growing since the early Jurassic, and in the late Jurassic they reach their most spectacular expression. Brachiosaurus, Diplodocus, Apatosaurus, Camarasaurus. These are animals so large they strain the imagination, creatures whose very existence seems to test the limits of what biology can achieve. Brachiosaurus is perhaps the most striking in visual terms. Where most sauropods have roughly horizontal backs with necks and tails extending at similar angles, Brachiosaurus has front legs distinctly longer than its hind legs, giving its body a slope like a giraffe's, with its neck rising almost vertically from its shoulders. An adult Brachiosaurus may have stood 12 meters tall at the top of its head, a height equivalent to a 4-story building. Its total length was perhaps 26 meters. Its weight is estimated at somewhere between 30 and 80 tons, a range that reflects the genuine difficulty of estimating the mass of an extinct animal from bones alone. Stand at the base of a Brachiosaurus and look up. The neck rises above you like a living tower, the skin rippled with the muscle beneath, the small head tilting this way and that as the animal reaches into the upper canopy of the conifer forest, pulling down branches with a mouthful of peg-like teeth. The sound it makes is not what we might expect. No roar, no dramatic call. Perhaps a low, resonant rumble felt more in the chest than heard with the ears. The ground trembles slightly beneath each footfall. The air around it carries the warm, heavy scent of an enormous herbivore, a smell like sun-warmed hay and something deeper, more animal. Nearby, a group of Diplodocus moves along the riverbank in the morning light. Diplodocus is a different animal from Brachiosaurus in almost every way that matters. Where Brachiosaurus is tall and front-heavy, Diplodocus is long and horizontally proportioned, built like a living suspension bridge. Its neck extends far out in front of its body, its tail, even longer, trails behind it, tapering to a thin whip-like tip. An adult Diplodocus may have been 27 meters long, but much of that length is neck and tail. Its body itself is relatively compact. The Diplodocus group moves slowly but steadily, following the riverbank. They do not hurry. Animals this large do not need to hurry. Their size alone is their primary defense against most predators, and even the largest predators of the Jurassic would need to be both hungry and courageous to attempt an attack on a healthy adult. They feed as they walk, pulling up ferns and low vegetation with their forward-facing teeth, sweeping their necks in slow arcs to maximize the volume they can reach without moving their enormous bodies. The young move in the center of the group. They are smaller, more vulnerable, kept close by the presence of the adults. A juvenile Diplodocus, perhaps 2 years old, pauses to investigate a patch of particularly lush fern, its movements quicker and less deliberate than the adults around it, its proportions slightly different, the neck not yet fully elongated, the body still a little rounded with youth. It has never known a world without these giants beside it. They are simply the landscape of its life. The water of the river is clear and cold, fed from the highlands. A family of smaller ornithopod dinosaurs drinks at the edge, lifting their heads frequently to scan the surroundings. Camptosaurus, a medium-sized plant eater capable of moving on 2 or 4 legs depending on the circumstances, its body compact and its tail held out behind it for balance. It is a cautious animal. Prey animals are always cautious. And they are right to be cautious, because in the shade of a large araucaria tree something watches them. Allosaurus, the apex predator of the Morrison Formation, the creature that has haunted the nightmares of the Morrison's herbivores for millions of years. It is not as large as the sauropods it sometimes hunts, but it does not need to be. It is 8 to 12 meters long, massively muscled through the hips and thighs, its forelimbs equipped with large recurved claws capable of gripping and holding prey. Its skull is large and powerful, reinforced with internal structures that may have allowed it to absorb the stresses of impact feeding, driving its upper jaw into prey like an axe rather than biting in the conventional sense. But right now, it is still, watching, its yellow-green eyes tracking the movements of the Camptosaurus at the water's edge with a patience that is almost meditative. Predation is not only about speed, it is about timing, about reading the landscape and the prey, and finding the moment when the investment of energy required to hunt will be most likely to produce a meal. The Camptosaurus drinks, the Allosaurus watches, the river moves past, the sauropods continue their slow walk along the far bank. And in the trees above all of them, creatures that are neither quite dinosaur nor quite bird flap and glide through the warm Jurassic air. Archaeopteryx, the famous transitional form, is present in this period, though it lived in what is now Germany rather than the Morrison. It is a creature at the exact boundary between 2 worlds, feathered like a bird, toothed like a reptile, clawed on its wings in a way that no living bird is. It represents not a dead end but a direction, the beginning of a lineage that will outlast all the giants below it. From high above, looking down on this Morrison world in the late afternoon light, the landscape is a mosaic of greens and browns and golds, the river winding through it like a silver thread. The shadows of the sauropods stretch long across the floodplain as the sun drops lower. The Allosaurus has moved on from its watching post, following some new scent, some new possibility. The Camptosaurus herd moves away from the water and into the shelter of the forest understory. The Jurassic evening settles over everything like a warm, heavy blanket. The insects begin their night chorus. Something calls from across the river, a sound low and resonant that carries far in the still air. The sauropods continue to move, unhurried, vast, their feet leaving deep impressions in the soft mud near the river that will remain, eventually as fossils embedded in rock, silent testimony to a world of giants. Rest now in this image, let the warm Jurassic air settle around you, let the sounds of that ancient evening grow distant and soft. The giants are all around you, enormous and gentle in the fading light, and the world is safe and still and wonderfully, enormously alive. The late Jurassic was not only about giants, it was also an age of extraordinary diversity at all scales. While the sauropods dominated the landscape in terms of sheer biomass, the world around them was full of smaller dramas, smaller lives played out with equal intensity. The stegosaurs were among the most distinctive animals of this world. Stegosaurus itself, the most famous of them, was a large plant-eater with a row of triangular bony plates running along its back in an alternating double row from neck to tail, and a tail tipped with 4 large spikes. What those plates were for is a question that has occupied paleontologists for decades. Were they for temperature regulation, providing surfaces for heat absorption or release? Were they for display, a visual signal to others of the same species? Were they defensive, making the animal appear larger to predators? The answer may be all of these things or none of them. Nature rarely builds structures for only one purpose. What we do know is that Stegosaurus was a successful animal, widespread in the Morrison Formation, its fossils found across a large area of the western United States. It was a gentle herbivore in behavioral terms, its small head and tiny brain suggesting a relatively simple inner life. It cropped low vegetation with its beaked mouth, moving slowly through the fern prairies and forest edges, its plates catching the afternoon sun. Its only real defense against Allosaurus was its tail. The spikes, which paleontologists call thagomizers after a Far Side cartoon, that achieved genuine scientific currency, were real weapons. Evidence from Allosaurus fossils shows healed puncture wounds consistent with Stegosaurus tail spikes, proof that these encounters happened and that sometimes the prey survived them. Life in the Jurassic was not peaceful in any simple sense. It was full of violence and hardship, of predation and competition, of disease and drought and flood. But it was also full of the quieter moments that make up most of any animal's life. The long hours of feeding, the warmth of the afternoon sun on armoured skin, the satisfaction of drinking cold river water after a long dry walk, the instinctive comfort of being among others of your own kind. These are the moments that the fossil record cannot capture. The joy of a juvenile sauropod discovering a particularly rich patch of vegetation, the drowsy contentment of a large predator lying in the shade after a successful hunt, the sharp alertness of a small theropod on a moonlit night, the whole nocturnal world spread out before it. We imagine them because we cannot help it, because we are animals too, and these are the things that matter in any animal's life, regardless of which age they inhabit. The Jurassic continues its long, warm, lush existence. Millions of years pass in their patient succession. The continents continue their slow drift. The climate shifts in slow cycles. Species appear, flourish, change, and sometimes vanish, replaced by descendants that are better suited to the slowly changing world. And somewhere in the Jurassic night, in the burrows and under the rocks and in the dense undergrowth where the large dinosaurs do not bother to look, the small, furry mammals continue their own quiet experiment. They have been here since the Late Triassic, evolving alongside the dinosaurs, mostly small and mostly nocturnal, mostly insectivorous, mostly overlooked. They do not yet know that their time is coming. They simply survive, as they have always survived, in the shadows of the giants. The Morrison Formation is one of the great gifts that geology has given to paleontology. Stretching across the American West in a continuous band of sedimentary rock, it preserves a remarkably complete picture of a single ecosystem that existed 150 million years ago. Paleontologists have been excavating its treasures since the 1870s, when the bone hunters of the Bone Wars, the famous rivalry between Othniel Charles Marsh and Edward Drinker Cope, were racing to outdo each other in the number and quality of their discoveries. That rivalry was not always conducted with the highest scientific ethics, but it produced an extraordinary flowering of dinosaur paleontology and gave the world some of its most famous species: Stegosaurus, Allosaurus, Diplodocus, Apatosaurus, all found in the Morrison, all bearing the marks of that era's fierce competition to name and describe new species. More than a century and a half later, the Morrison continues to yield new discoveries. New species are still being named. New specimens are still being found that add detail and nuance to our picture of this late Jurassic world. Each new discovery is a window that opens a little wider, letting in a little more light on a world that existed so long ago it almost seems like mythology. But it was not mythology, it was real. The footprints are still there, pressed into rock that was once soft Jurassic mud. The bones are still there, buried in sediments that have preserved their shape for 150 million years. The evidence of lives lived is incontrovertible. Let us walk through the Morrison more slowly, attending to the details that make this world not just spectacular but real. The climate of the Morrison was distinctly seasonal. During the wet season, the rivers ran full and the floodplains were green and productive. During the dry season, the landscape became significantly drier, the vegetation sparser, the rivers reduced to chains of pools connected by stretches of dry gravel. Many of the Morrison dinosaur bone beds, accumulations of bones from multiple individuals, appear to have formed during the dry season, when animals congregated around the remaining water sources. When those water sources failed entirely, or when they shrank to the point that the congregation of animals exceeded what the limited habitat could support, mass deaths occurred. Picture a dry season waterhole in the Morrison, late in the dry season. The ground around the water is trampled to bare, cracked mud. The smell of the place is strong with the accumulated presence of many large animals over many months. The vegetation within a kilometre has been stripped or trampled, yet still the animals come because there is nowhere else to go. Camarasaurus, the stout-bodied, large-headed sauropod, stands in the shallows, drinking deeply. A group of Stegosaurus occupies a patch of shade nearby. Smaller ornithopods cluster nervously at the water's edge, drinking quickly and moving away from the larger animals. And watching all of it from a distance, a large Allosaurus regards the scene with the patient intelligence of an apex predator that has learned that desperation brings opportunity. The dry season always produces more vulnerable animals, the calves that have lost condition, the old animals that can no longer compete effectively for food, the juveniles separated from the protection of the herd. Patience, at this time of year, is the most important hunting skill. The Jurassic ecosystem, like all ecosystems, was driven by these rhythms of abundance and scarcity, of wet and dry, of growth and decline. The enormous biomass of sauropods that the Morrison supported was possible because of the extraordinary productivity of the wet season, the lush vegetation that grew rapidly in the warm, well-watered months, and that these animals consumed with equally extraordinary efficiency. But the dry season imposed its own checks, its own mortality, its own regulation of population sizes. The sauropods of the Morrison were not all the same. They occupied different parts of the food web, feeding at different heights, in different habitat types, at different times. Diplodocus, with its low horizontal neck, may have fed primarily at ground level, sweeping up ferns and low vegetation. Brachiosaurus, with its tall front-heavy body and long, nearly vertical neck, fed in the upper canopy of the conifer forests. Camarasaurus, with a shorter, more robust neck, may have been more of a generalist, feeding at intermediate heights. This partitioning of resources reduced direct competition between the species and allowed multiple large sauropods to coexist in the same landscape. Modern ecosystems show the same principle. Different species of a large herbivore in the African savanna feed at different heights, in different habitat types, or at different times of day, reducing competition and allowing more species to coexist than would otherwise be possible. The Jurassic dinosaurs had apparently discovered this principle independently, or rather natural selection had shaped their ecologies in response to the same fundamental competitive pressures that shaped the modern African herbivores. The predators of the Morrison were likewise diverse. Allosaurus was the dominant large predator, but it was not alone. Ceratosaurus, with its unusual horn on the snout, was a contemporary and potential competitor. Torvosaurus, one of the largest theropods of the Jurassic, may have been the apex predator in some Morrison habitats, large enough to tackle even subadult sauropods. Smaller theropods like Ornitholestes and Coelurus filled the niches for medium and small predators, hunting the lizards and small dinosaurs and mammals and insects that the large predators ignored. And in the night, while the large predators rested and the great herds of herbivores stood vigilant or slept in rotating shifts, the smallest inhabitants of the Morrison world went about their business. The early mammals, tiny and shrew-like, emerged from their daytime hiding places to hunt insects in the dark. The small nocturnal reptiles moved through the undergrowth with quick, silent efficiency. Moths and beetles and countless other insects navigated the darkness by instinct and moonlight. The Jurassic night was full. Every darkness is full if you know where to look. Every silence is full of small sounds. Every apparent emptiness contains a world. Rest in that fullness now. The darkness of the Jurassic, warm and complete and full of small alive things. The stars above the Morrison visible with a clarity impossible in our light-polluted world. The Milky Way a visible band of light stretching from horizon to horizon. The air smelling of warm earth and vegetation, and the faint, rich animal smell of many large bodies nearby. You are very still. The ancient night is all around you, and somewhere in the distance something very large is breathing in the dark. We have spoken of the sauropods in broad strokes, mentioning their size, their long necks, their importance in the Jurassic world, but the sauropods deserve more than broad strokes. They were among the most extraordinary animals in the history of life, and the details of their biology are a source of ongoing fascination and active research that continues to yield surprises. The largest sauropods, those that have been measured at lengths of 30 meters or more and estimated weights of 50 to 70 tons, were pushing against what appears to be the physical limits of what a land animal can be. The engineering challenges involved in being that large are profound and numerous. Structural support, thermoregulation, the pumping of blood from a heart at ground level to a brain that might be 10 or 12 meters above it. The processing of sufficient food to fuel a metabolism of that scale, the simple mechanics of locomotion at that mass. Each of these challenges has its own solution, or its own set of solutions, and the sauropod body plan is a record of those solutions accumulated over millions of years of evolution. The structural challenge is addressed by the architecture of the sauropod skeleton in ways that are elegant and which modern engineers have studied and admired. The vertebrae of the largest sauropods are not solid bone. They are extensively pneumatized, meaning they contain a network of air spaces that reduce their weight while maintaining their structural integrity. This pneumatization is directly comparable to the pneumatized bones of modern birds, and it is driven by the same biological system: air sacs connected to the respiratory system that invade and hollow out the bone during development. A sauropod vertebra is like a biological version of a foam-filled structural panel, strong in compression and resistant to bending while being much lighter than solid bone would be. The long neck of the sauropods is often presented as simply a feeding adaptation, allowing the animal to reach vegetation that other herbivores could not access. And it is that. But it is also a thermoregulation device. A large body generates enormous amounts of heat as a byproduct of metabolism and muscular activity. That heat must be dissipated or the animal overheats. The long neck and tail provide enormous surface area relative to volume, acting as heat exchangers that allow the animal to radiate excess heat to the environment. The surface area of a diplodocus neck alone was comparable to the surface area of several modern elephants. The heart question is one that has generated considerable discussion. To pump blood from a heart at shoulder height to a brain at the top of a 12-meter neck would require either an extraordinarily high blood pressure or an accessory pumping mechanism of some kind. Some researchers have proposed that sauropods had multiple hearts along the neck, auxiliary pumps that boosted blood pressure at intervals along the route from chest to brain. Others have proposed that the neck posture was typically held more horizontally than the popular images suggest, reducing the vertical distance the blood had to travel. The question is still open, and its resolution will require better data on the internal soft tissue anatomy of sauropods than the fossil record currently provides. The feeding challenge for a sauropod is almost incomprehensible in its scale. A large sauropod needed to process hundreds of kilograms of vegetation every day just to maintain its body weight and fuel its metabolism. The teeth of most sauropods are simple peg-like or spatula-like structures with limited chewing ability. They were not grinding their food the way a cow or a horse grinds food. They were cropping it and swallowing it with minimal processing, relying on a long fermentive gut to break it down chemically. This swallow and ferment strategy is common in large herbivores. Modern elephants use it, as do cattle and horses to varying degrees. The limitation is that fermentation is slow, and the gut capacity required to process enough food this way is enormous. A sauropod's digestive system must have occupied most of its barrel-shaped body, a vast, warm, microbe-filled chamber where the plant material was slowly broken down and the nutrients extracted. The locomotion of the largest sauropods is another area of active research. At their mass, the energetics of movement are critical. Every step of a 50-ton animal requires substantial energy, and the cumulative cost of locomotion over the course of a day is a significant fraction of the animal's total energy budget. Analysis of sauropod trackways suggest that they moved in a slow, steady, energy-efficient manner, their footfalls placed with a deliberate precision that minimized the energy wasted in lateral swaying. They were, in other words, economical movers, their enormous bodies engaged in a constant negotiation with gravity and energy. The speed of the largest sauropods was necessarily limited. Biomechanical analysis suggests that an animal of the mass of the largest titanosaurs could not have moved faster than about 10 to 15 kilometers per hour without risking stress fractures in its leg bones. This is not particularly slow in absolute terms, faster than a brisk human walk, but it is slow relative to the large predators of the same environments, some of which could move at twice that speed in short bursts. How then did the giant sauropods protect themselves from predators? The answer appears to be multifaceted. Size itself is a deterrent. An animal of 50 tons is simply too large for most predators to attack safely, even for the largest theropods. The tail of many sauropods, long and heavy and capable of being swung with considerable force, was a weapon in its own right. Diplodocid sauropods had particularly long, thin tails that may have been used like whips, the tip moving faster than the speed of sound and producing a crack audible from a great distance, in defense or in interspecific communication. Social behavior also provided protection. Many sauropod bone beds suggest gregarious behavior, and moving in groups provides collective vigilance and mutual defense. A predator approaching a group of Apatosaurus would have to contend with multiple large, potentially dangerous animals rather than a single isolated target. The reproduction of the giant sauropods was, by necessity, a numbers game. A 50-ton animal cannot protect its eggs in the way that a much smaller animal can. The investment in any individual egg is therefore small relative to the total reproductive investment, and the strategy appears to have been to produce large numbers of small eggs, and allow most of the hatchlings to fend for themselves. Sauropod eggs are remarkably small relative to the adults, typically the size of a large grapefruit, and hatchlings were tiny compared to their parents, perhaps 50 centimeters long from animals that would eventually reach 25 meters. This means that juvenile sauropods occupied completely different ecological niches from adults, being small and vulnerable in ways that the adults were not, and growing at extraordinary rates to reach the relative safety of large body size as quickly as possible. The growth rings preserved in sauropod bone show growth rates that are among the fastest known for any vertebrate, the largest species adding tons of body mass per year during their peak growth phase. A sauropod's life, then, was a trajectory from extreme vulnerability to extreme invulnerability, from a tiny hatchling hiding in the undergrowth to a giant moving through the landscape with the unhurried confidence of an animal that nothing can harm. It is one of the most dramatic individual transformations in the animal kingdom, and it took place over decades. The slow accumulation of bone and muscle and sheer biological mass that eventually produced one of the most impressive creatures the Earth has ever seen. Stand in the imagined presence of a large sauropod for a moment. Not the reconstruction in a museum, all bones and scaffolding. The real animal, the living animal, its skin warm and textured, perhaps patterned in ways we cannot know, its breath audible at close range, a slow, deep rhythm, the ground trembling faintly as it shifts its weight, the air carrying the warm animal smell of it, rich and complex, the scent of a living body on a scale you have never encountered. It does not see you as a threat. You're too small to register as anything significant. Perhaps it notes your presence with one large patient eye, the same eye that notes the presence of birds picking parasites from its flanks, or the same eye that registers the movement of the river in the afternoon light. And then it looks away, because it has eating to do, and the ferns within reach of its neck are excellent today, and the afternoon is warm and pleasant, and life is very good if you are a sauropod in the middle of the Jurassic. Very good indeed. Let that warmth into you, the Jurassic afternoon, the smell of ferns and warm earth, the immense, peaceful presence of the largest land animal that has ever lived, feeding contentedly in the golden light. You are small beside it, and safe, and very still. And the world around you is impossibly ancient and impossibly alive. Rest now in the size of things, in the extraordinary scale of this world, in the patience of time. The giants are feeding, the light is fading, the day is ending. And everything is exactly as it should be. Let us linger a while longer in the Jurassic. It deserves more time than we have given it, this longest and most stable chapter in the dinosaur story. 145 million years of warm, relatively stable climate. 145 million years in which the dinosaurs had the world largely to themselves, and the time to develop the most spectacular fauna of large land animals the Earth has ever seen. The diversity of theropods in the Jurassic is remarkable. While Allosaurus was the dominant large predator in the Morrison Formation, other theropod lineages were experimenting with different approaches to the predatory lifestyle across the globe. In China, in the deposits of the Shaximiao Formation, animals like Sinraptor and Yangchuanosaurus occupied similar ecological roles to Allosaurus, in a very different geographic context. These animals had evolved independently of the North American lineage, following the same general evolutionary trajectory of large bipedal predator, but arriving at somewhat different solutions to the same basic challenges. The Coelurosaurs, the lineage that would eventually give rise to the birds, were present in the Jurassic in remarkable diversity. These were smaller, faster, more cognitively sophisticated animals than the large carnosaurs, and they were exploring a wide range of ecological niches. Some were insectivores, some were small vertebrate hunters, some may have been at least partially herbivorous, their guts capable of processing plant material as well as animal protein. The ecological flexibility of the coelurosaurs was the foundation of the extraordinary diversification that this lineage would achieve in the Cretaceous. The Ornithischian dinosaurs, the group that would produce the spectacular armoured and horned and crested forms of the Cretaceous, were present in the Jurassic but had not yet reached their full expression. The ornithopods, the ancestors of the hadrosaurs, were small to medium-sized bipedal herbivores, capable runners that relied primarily on speed and agility for defence. The early thriophorans, the lineage that would produce the stegosaurs and eventually the ankylosaurs, were present as well, their body armour already established as the primary defensive strategy. The stegosaurs were one of the characteristic animals of the Jurassic, and their distribution was nearly global. Stegosaurid fossils have been found in North America, Europe, Africa and Asia, and the group appears to have been extraordinarily successful during the Jurassic before declining and eventually disappearing in the Cretaceous. The reason for their decline is not fully understood. The rise of the more efficient hadrosaurs and other ornithopods, which could process vegetation more effectively than the stegosaurs, may have gradually displaced them from the large herbivore niches they had occupied. The Jurassic world had a particular quality of ecological stability that the Cretaceous would not fully replicate. The slower pace of evolution in a stable world, the long tenures of individual lineages in established ecological roles, the accumulation of complex community relationships over tens of millions of years, all of this produced ecosystems of extraordinary integration and interdependence. The Morrison ecosystem at its peak was not just a collection of species, but a community that had been developing and refining its internal relationships for millions of years. The rivers of the Morrison were full of fish, including early teleosts, the group that today contains virtually all familiar fish species. These fish were prey for the crocodilians that patrolled the river margins, for the pterosaurs that fished from the air, and possibly for some of the dinosaurs as well. The idea of dinosaurs as fish-eaters has been gaining support in recent years, with the discovery of spinosaurids and other theropods that appear to have been at least semi-aquatic and dependent on fish as a major food source. Baryonyx, from the early Cretaceous of England, was found with fish scales and fish bones in its stomach region, direct evidence of fish eating. Spinosaurus, the largest of all known theropods, from the late Cretaceous of North Africa, has been reinterpreted in recent years as a primarily aquatic or semi-aquatic animal, its dense bones reducing its buoyancy and allowing it to wade into rivers in search of large fish. These discoveries have expanded our understanding of dinosaurian ecology considerably, revealing that the theropods occupied aquatic niches that had not been previously appreciated. The Jurassic world continues its long, unhurried turning. Season follows season. The wet season brings the rivers to life and the floodplains green. The dry season contracts the world around the remaining water. And in this rhythm, generation follows generation, each one living out its brief portion of the enormous span of Jurassic time. A stegosaurus that lived its 20 or 30 years at the peak of the Morrison ecosystem never knew anything beyond its small corner of that world, its territory, the specific rivers and forests and fern prairies it knew from birth, the individuals of its own species that shared that space with it, the predators it had learned to fear, the food sources it returned to season after season. This was its world, complete and whole, and sufficient for everything it needed to be. And that is the Jurassic in its deepest truth, not a spectacle for our astonishment, though it is that, but a world of complete and sufficient lives, each one real in itself, each one asking nothing more of existence than to continue, to eat and move and rest and occasionally encounter another creature with enough calm to allow the encounter to pass without violence. The deep Jurassic afternoon is timeless. Let yourself be there in it just for a moment. The warm air, the sound of the forest, the distant river, the enormous patient animals moving through it all with the unhurried certainty of creatures that have all the time in the world. Because they do. The Jurassic is 145 million years long. They have time. And so, just for now, do you? The dinosaur story is so dominated by its giants that it is easy to forget how diverse the smaller end of the spectrum was. Not every dinosaur was enormous. Not every dinosaur aspired to be. Some of the most evolutionarily successful, most ecologically important and most biologically interesting dinosaurs were small, sometimes tiny, and they inhabited a world that the giants barely noticed. Microraptor from the early Cretaceous of China was a small dromaeosaurid with an extraordinary feature. It had feathers not just on its arms but on its hind legs as well, creating a four-winged structure that was unlike anything in the modern world. How it flew, or whether it flew in the powered sense rather than gliding, is still debated. But the image of a four-winged dinosaur is one of the most striking in paleontology, a reminder that evolution explores possibilities we would not have predicted, tries combinations we would not have imagined. Parvicursor from the late Cretaceous of Mongolia was barely 30 centimeters long and weighed perhaps 100 grams, comparable to a modern sparrow. It was an alvarezsaurid, a bizarre lineage of small theropods with tiny vestigial forelimbs, bearing a single large claw that may have been used for breaking into insect nests. The alvarezsaurids are one of the stranger evolutionary experiments of the dinosaur lineage. Their reduction of the forelimbs to near uselessness, convergent in some ways with the reduction seen in Tyrannosaurus, but from a completely different starting point and producing a completely different result. Yiqi, another small feathered dinosaur from the Jurassic of China, had something even stranger than Microraptor's four wings. It had a rod-like bone projecting from its wrist that supported a membrane, creating a wing more like a bat's than a bird's. No living bird has such a structure. Nothing in the modern world is quite like Yiqi. It was an evolutionary experiment that apparently went no further, its distinctive wing structure not giving rise to any successful descendants, simply one of evolution's many ideas that did not persist into the long term. These small dinosaurs are important for our understanding of the dinosaur story in several ways. They demonstrate the breadth of ecological space that the dinosaurs occupied, from the enormous sauropods to animals barely distinguishable from large insects in terms of body size. They demonstrate the evolutionary creativity of the lineage, the willingness of natural selection to try combinations that seem improbable from our hindsight perspective, and they demonstrate that the small and the overlooked are often doing the most evolutionarily interesting things, while the giants attract all the attention. The fossil record is biased toward large animals. Large bones are more likely to be preserved, more likely to be found, and more likely to be noticed once exposed. The small dinosaurs are underrepresented in our understanding of the Mesozoic world, and the true diversity of the smaller size classes was almost certainly much greater than what we have found. For every small dinosaur species we know, there may have been many that left no fossil record at all, their tiny bones too fragile and too easily destroyed to survive even the best preservational conditions. This should humble us. The story we are telling tonight is the story as best we can reconstruct it from the evidence available. The real story, the complete story, is richer and stranger and more diverse than anything we can know. There are whole lineages we have never heard of because they left no trace we can find. There are behaviors and ecological relationships and evolutionary experiments that are simply gone, as completely gone as if they had never existed, because the conditions that would have preserved their evidence never came together. The dinosaur world was larger than our knowledge of it. The real Jurassic was richer than the Morrison Formation can tell us. The real Cretaceous was more diverse than the Hell Creek and Gobi and Wealden, and all the other famous formations combined. We see the world through the filter of what happened to be preserved, and that filter has removed most of what there was to see. What remains is still extraordinary. What we have found in all the fossil beds of all the continents is still enough to fill a story as long as this one with room to spare. The giants and the tiny, the predators and the prey, the armoured and the swift and the brilliantly coloured and the night hunting and the polar and the aquatic and every other form that the dinosaur body plan could be bent into across 180 million years. It is a great and irreplaceable richness. It is gone as a specific realised world, but it is not entirely lost because we can find it in the rocks and read it with the tools of science and bring it back, imperfectly, incompletely, but genuinely, in the mind's eye of any human being patient enough to look. You have been patient enough to look tonight, and you have seen something real. Not everything, never everything, but something real and true and extraordinary. Rest in that seeing, let it be enough. The Cretaceous period begins approximately 145 million years ago, and it will last until 66 million years ago, an astonishing span of nearly 80 million years. To put that in perspective, Our entire evolutionary lineage from the first upright walking human ancestors to the present day spans only about 7 million years. The Cretaceous is 11 times longer than that. It is an age of extraordinary duration, and within it, the dinosaurs achieved their greatest diversity, their most spectacular forms, their most elaborate evolutionary experiments. The world of the Cretaceous is different from the Jurassic in important ways. The supercontinent of Pangaea has now largely broken apart. The Atlantic Ocean, just a narrow seaway in the late Jurassic, has been widening for millions of years, separating the Americas from Europe and Africa. The continents are beginning to look more like the geography we know, though the differences remain profound. Shallow inland seas flood portions of what will be North America and Europe. The global climate is still warmer than today, warmer in many parts than the Jurassic was. Sea levels are high, the poles are cool but not frozen. And something else is changing that will shape the world in ways no dinosaur can anticipate. The flowering plants are evolving. For nearly all of the history of plants, the dominant vegetation had been non-flowering. Conifers, cycads, ferns, horsetails, mosses. Green and nutritious and effective at photosynthesis, but reproductively conservative, relying on spores or wind-pollinated cones to spread their genetic material. The earliest flowering plants, the angiosperms, appear in the fossil record in the early Cretaceous, and they bring with them a revolution. Angiosperms are better at attracting pollinators. Their flowers are structures built specifically to facilitate the exchange of pollen, not by wind alone, but by the bodies of insects and eventually other animals that visit them for nectar. This creates a relationship, a mutual dependency, between plant and pollinator that accelerates the evolution of both. As flowering plants diversify, they produce new flower shapes, new colours, new scents, each one fine-tuned to attract particular kinds of visitors. And the insects that visit them evolve in response, their mouthparts and bodies and behaviours shaped by the flowers they depend on. By the middle and late Cretaceous, flowering plants are diversifying explosively. The first grasses will not appear until near the end of the Cretaceous, but flowering trees and shrubs and ground-covering plants are spreading across the landscape. The world begins to smell different, to look different. The uniform greens of the Jurassic give way to a patchwork of colours and textures, as flowering plants add their variety to the vegetation. The dinosaurs must adapt to this changing world, and they do. They always have. It is in the Cretaceous that we meet some of the most remarkable dinosaurs that ever lived. The ornithischian plant-eaters, the group that includes the horned and armoured and crested and duck-billed dinosaurs, reach their greatest diversity here. And in the theropod lineage, evolution is quietly doing something extraordinary, producing the animals that will eventually give rise to the birds. Let us walk through the Cretaceous world slowly, taking the time to look at what is there. The hadrosaurs, commonly called the duck-billed dinosaurs, are among the most successful herbivores the world has ever seen. They are medium to large ornithopods with broad, flattened snouts and batteries of teeth that are among the most sophisticated grinding structures ever evolved in a land vertebrate. A hadrosaur's dental battery contained hundreds of teeth packed tightly together in a self-sharpening arrangement. As the teeth at the surface wore down, new teeth moved up from below to replace them. At any given moment, a hadrosaur might have had hundreds of teeth in active use. This extraordinary dental machinery allowed them to process tough vegetation, including cycads, conifers, and the newly abundant flowering plants with an efficiency no other dinosaur could match. Parasaurolophus is one of the most visually striking hadrosaurs. It carries on its head an elaborate hollow crest that curves up and back from above the nostrils, extending well beyond the back of the skull. The internal structure of this crest is a series of connected tubes that form a resonating chamber. By forcing air through these tubes, Parasaurolophus could produce deep, resonant calls that would have carried for remarkable distances across the late Cretaceous landscape. Different species had differently shaped crests, suggesting that the specific acoustic properties of the crest played a role in species recognition, perhaps also in mate attraction. Imagine a herd of Parasaurolophus moving through a late Cretaceous forest of flowering trees and conifers. The ground is soft beneath their feet, the soil dark and rich after the wet season. They move with the cautious alertness of prey animals, their heads rising frequently to scan the forest around them. And as the herd calls to one another, as individuals communicate their positions and states and intentions, the sound that fills the forest is extraordinary, deep, resonant, almost musical in its quality. It reverberates between the trees, seems to come from everywhere at once, fills the air with a vibration felt as much as heard. You hear it now, if you let yourself, there in the quiet space behind your closed eyes, that deep, calling note, carrying across 100 million years, still resonant, still full of life. The armoured dinosaurs, the ankylosaurs, reached their most impressive expression in the Cretaceous. Ankylosaurus itself, appearing near the very end of the period, is one of the most heavily armoured animals in the history of land life. Its upper body is covered in a mosaic of bony plates called osteoderms, embedded in the skin and providing a layer of protection that even a Tyrannosaurus would struggle to penetrate. Its tail ends in a large, heavy club of fused bone that could be swung with enough force to break the leg of an attacking predator. It moves slowly, a deliberate, grounded animal that does not flee, but faces what comes with the solid certainty of a creature encased in its own armour. The ceratopsians, the horned dinosaurs, are another group at their most spectacular in the Cretaceous. Triceratops, the most famous of them, will appear near the very end of the period, but the ceratopsian family includes dozens of species across the Cretaceous, each with its own arrangement of horns and frills, each exploring a slightly different variation on the basic theme of ornamentation. Why horns? Why frills? The question has occupied paleontologists for decades, and the answer appears to be complex. Horns are clearly capable of defense, and evidence exists for their use in combat with predators. But the elaborate frills, richly supplied with blood vessels and possibly brilliantly coloured in life, seem more likely to have been primarily display structures. Animals recognise each other by their crests and frills and horns. Potential mates assess fitness. Rivals gauge each other's strength before committing to costly physical confrontation. The Cretaceous is, in many ways, a world of communication. Hadrosaurs calling across the forest, ceratopsians displaying their finery to one another, theropods producing sounds we can only guess at. The dinosaurs are not silent mechanical animals. They are communicating social creatures navigating a world of relationships as complex in their own way as any that exists today. In the forests of what will one day be the Gobi Desert in Asia, a very different kind of drama is unfolding. The Cretaceous of Central Asia is a place of contrasts, lush during the wet season, harsh during the dry, rich in fossils that have been revealing their secrets to paleontologists since the 1920s. Here, in the fine-grained sandstones that preserve animals in extraordinary detail, we find some of the most famous dinosaur discoveries ever made. Velociraptor. The name has been distorted by popular culture into something larger and more dramatic than the actual animal. But the real Velociraptor is remarkable enough in its own right. It is the size of a large turkey, perhaps 70 centimetres tall at the hip, its most distinctive feature the enlarged sickle-shaped claw on each second toe. This claw was not used for slashing as popularly depicted. Evidence suggests it was more likely used for gripping and pinning prey, holding it down while the animal used its jaws to deliver killing bites. Velociraptor almost certainly had feathers. We know this not from direct fossil evidence of Velociraptor itself, but from the closely related genuine long and the presence of quill knobs on the forearm of at least one Velociraptor specimen, clear evidence of feather attachment. It was a feathered animal, and in life it would have looked far more bird-like than the scaly, lizard-like creature that popular culture prefers. Picture it then, as it really was. A feathered animal, perhaps brown or reddish bronze, its plumage ruffled slightly by the desert wind. It stands on the edge of a low scrub, its large eyes scanning the landscape with the sharp focus of a hunter. Its tail holds horizontally behind it, its head low, its posture that of an animal intensely focused on something in the scrub ahead of it. Whatever it is hunting, it has not yet decided to move. Patience is a virtue for predators as much as for meditators. The Cretaceous world is full of such moments, full of the patient intensity of hunters and the nervous alertness of prey, full of the slow, deliberate feeding of great plant-eaters and the complex social interactions of herding animals, full of the calling of hadrosaurs and the thundering of ceratopsian herds and the barely visible scurrying of small mammals through the undergrowth. And above it all, the sky is full of pterosaurs, the flying reptiles that have been mastering the air since the Triassic, now reaching their most spectacular forms. Quetzalcoatlus, from the late Cretaceous of North America, may have been the largest flying animal in Earth's history, with a wingspan estimated at 10 to 11 meters and a standing height similar to a giraffe. It likely spent much of its time stalking across open ground on all fours, using its enormous beak to snap up small dinosaurs and other prey, and taking to the air when distance or wind conditions made flight more efficient than walking. The sky of the late Cretaceous, with these enormous pterosaurs wheeling overhead, and the first modern birds beginning to populate the trees and shorelines, would have been an astonishing sight. A sky full of life. A sky that looked almost familiar, if you squinted, if you let your eyes blur slightly and forgot for a moment how long ago it was. Let your eyes close now, just a little. Let the Cretaceous sky form behind them, the warm blue air, the vast slow circles of the great pterosaurs, the distant calling of things you cannot name, the world enormous and alive and ancient and still so very, very far from its ending. The evolution of flowering plants during the Cretaceous was one of the most consequential events in the history of life. The angiosperms, as the flowering plants are technically called, had a key advantage over the conifers and cycads that had previously dominated. They could recruit animals as pollinators and seed dispersers in ways that wine-pollinated plants could not. A flower is not just a beautiful structure, it is a communication device. Its colours, shapes, and scents are signals directed at specific audiences, the insects, birds, and other animals that the plant has, over millions of years of coevolution, learned to attract and exploit. The plant offers nectar or pollen as a reward. The animal, in collecting that reward, inadvertently transfers pollen from one flower to another, enabling fertilization without the hit-or-miss randomness of wind pollination. The arrangement is mutually beneficial. It is also remarkably efficient. A plant that can target specific pollinators wastes far less pollen than one that simply releases it into the wind and hopes for the best. The consequences of this revolution rippled through every ecosystem. As flowering plants diversified and spread, the insects that pollinated them diversified too. Bees, wasps, butterflies, beetles, flies, each group expanding and diversifying in response to the expanding variety of flowers. And as insects diversified, the animals that ate insects diversified. Small lizards, small mammals, birds. Every level of the food chain was affected by what had started as a change in how a plant reproduced. The dinosaurs felt the effects too, though more indirectly. As flowering plants spread into habitats previously dominated by conifers and cycads, the herbivore fauna that depended on those plants had to adjust. Some species that had been well adapted to feeding on conifers found the new vegetation less suitable. Others found themselves with access to new food sources that their competitors had not yet exploited. The composition of dinosaur communities shifted during the Cretaceous in ways that may partly reflect the changing vegetation. The hadrosaurs, with their extraordinarily sophisticated dental batteries capable of processing tough vegetation of many types, were ideally positioned to exploit the diverse array of plants that the angiosperm revolution produced. Their success in the late Cretaceous may in part be attributable to their dietary flexibility, their ability to feed on whatever was available, rather than being locked into a narrow specialist diet. The ceratopsians, too, with their powerful beaks and shearing cheek teeth, were capable of processing tough vegetation efficiently. The frill and horn system that makes them so visually spectacular was primarily a communication device, used in the intraspecific signalling that is so important in highly social animals, but the chewing apparatus was the real key to their success, the biological machinery that turned the diverse Cretaceous vegetation into the energy and nutrients that fueled their extraordinary diversity. It is worth pausing to appreciate what it means for the same basic body plan to produce such astonishing variety within a single geological period. The ceratopsian family, from the earliest hornless forms to the elaborate horn and frill arrangements of Triceratops and its relatives, spans a range of morphological variation that rivals the entire diversity of the bovid family in modern Africa, and yet they all share the same fundamental features: the beak, the frill, the basic body proportions, evolution working the same theme over and over, but each time producing something new. The same principle applies across the dinosaurs as a whole. The theropods, from the tiny Microraptor barely the size of a crow to the colossal Spinosaurus at perhaps 15 meters or more in length, all share the same fundamental bipedal hollow-boned theropod body plan. The sauropods, from the modest Europasaurus, an island dwarf whose isolation on a Cretaceous archipelago caused it to evolve a smaller body size, to the enormous Patagoteton at over 30 meters and perhaps 70 tons, all share the same elongated four-legged long neck design. Variation within a theme. It is what evolution does. It works with what it has, modifying the existing rather than creating new from nothing. And the range of variation that can be produced from a single starting point over millions of generations is a thing of extraordinary beauty. The Cretaceous was also an age of extraordinary geographic diversity among the dinosaurs. The breakup of the continents that had been proceeding since the Triassic had, by the late Cretaceous, produced essentially separate faunas on the different landmasses. North American dinosaurs were different from South American dinosaurs, which were different from European dinosaurs, which were different from Asian dinosaurs, which were different from the dinosaurs of the southern continents. Each landmass was its own evolutionary experiment, shaped by its own climate, its own vegetation, its own unique combination of ecological pressures. The Asian dinosaurs of the late Cretaceous, from the Gobi Desert beds of Mongolia and China, are in some ways the most fascinating. This region has produced an extraordinary variety of small to medium-sized theropods, many of them beautifully preserved with evidence of feathers and other soft tissue. Oviraptor, initially named as an egg thief, based on a misidentification of the eggs it was found with, but now understood to have been brooding its own nest, a beautifully bird-like behaviour. Protoceratops, the small ceratopsian found in such extraordinary numbers that its nesting sites were well known before the eggs were correctly identified. The dromaeosaurids, the raptor family, represented in Asia by numerous species and showing a diversity of sizes and apparent ecologies. And the fossils of Asia tell stories beyond mere taxonomy. The fighting dinosaurs specimen, a velociraptor and a protoceratops preserved in the act of combat, is one of the most extraordinary fossils ever found. Two animals frozen in a moment of struggle that occurred approximately 80 million years ago, their bones tangled together in a posture that speaks directly to the reality of predator and prey in the ancient world. The velociraptor's killing claw embedded in the neck of the protoceratops. The protoceratops' beak clamped around the velociraptor's forearm. A struggle that ended in death for both, probably when a sandstorm or collapsing sand dune buried them as they fought. Looking at that fossil, you are looking at a real moment. A Tuesday afternoon 80 million years ago. Two real animals with real hunger and real pain and real determination. Not symbols, not abstractions, just life, in the most immediate and uncompromising sense. That is what the fossils give us if we let them. The reality behind the distance, the warm blood behind the cold stone. While the dinosaurs ruled the land and the pterosaurs mastered the sky, the seas of the Mesozoic were developing their own extraordinary cast of characters. The oceans of the Triassic, Jurassic and Cretaceous were not the same oceans that exist today, and the life they contained was in many ways as spectacular as anything that walked on land. The Triassic seas were still recovering from the Great Dying when the dinosaurs were first appearing on land. The great reef ecosystems of the Permian had been largely destroyed, their complex architecture of corals and sponges and invertebrate life swept away by the acidification and warming that the volcanic eruptions had caused. The early Triassic Ocean was, in many of its regions, a simplified, reduced ecosystem, dominated by disaster fauna, the small, opportunistic species that colonize disturbed environments before more complex communities can establish themselves. But by the Middle Triassic, the seas were recovering. New coral reefs were establishing themselves, built by different coral species from those that had dominated the Permian. New groups of marine animals were appearing and diversifying, and among the most spectacular of those new groups were the marine reptiles. The ichthyosaurs were among the first truly large marine reptiles of the Mesozoic, and they are in many ways its most visually dramatic. These were entirely aquatic animals, their limbs transformed into flippers, their bodies streamlined to an extraordinary degree, their eyes enormous for seeing in the deep ocean. The largest ichthyosaurs were comparable in size to the largest modern whales. Shonisaurus from the Triassic of Nevada, one of the largest known, may have been 15 meters or more in length, and some fragmentary remains suggest that the largest ichthyosaurs may have exceeded 20 meters, making them among the largest animals that have ever existed. The ichthyosaurs evolved their streamlined, dolphin-like body form through a process of convergent evolution, similar to what would later produce dolphins and whales from mammalian ancestors. The similarities between an ichthyosaur and a dolphin are striking and extend well beyond overall body shape. Both have a dorsal fin. Both have a tail fin for propulsion, though the ichthyosaur tail is vertical rather than horizontal. Both have large binocular eyes positioned toward the front of the skull. Both were warm-blooded, maintaining a high body temperature independent of the surrounding water, a necessary adaptation for the kind of fast, sustained swimming they engaged in. The ichthyosaurs were obligate aquatic animals, giving birth to live young rather than returning to land to lay eggs. We know this because some ichthyosaur fossils are preserved in the act of giving birth, the infant emerging from the mother's body in a posture that could only result from live birth rather than egg-laying. These extraordinary fossils are both scientifically valuable and unexpectedly moving, a mother and offspring frozen together in their final moment in a silent testimony to the fact that the care of young is ancient beyond any telling. The plesiosaurs were the other great group of Mesozoic marine reptiles, and they represent a very different approach to life in the ocean. Where the ichthyosaurs were built for speed, the plesiosaurs were built for maneuverability. Their broad bodies, supported by two pairs of large, powerful flippers that acted like underwater wings, could turn with exceptional agility, allowing them to pursue fish and cephalopods through the complex three-dimensional space of the open ocean. The plesiosaurs split into two main groups early in their history. The long-necked forms, the plesiosaurs in the strict sense, had enormously elongated necks, sometimes with more than 70 vertebrae, more than any other known vertebrate. Their small heads were equipped with sharp, interlocking teeth ideal for catching slippery fish. Their long necks allowed them to approach prey from unexpected angles, darting the head through the water to snatch fish that had not detected the approach of the larger body. The neck was flexible, but not as flexible as popular depictions often suggest. It could not raise high above the water and arch like a sea serpent, but it could extend forward and to the sides in ways that gave its owner a significant hunting advantage. The pliosaurs, the short-necked plesiosaurs, took the opposite approach. Where the plesiosaurs had small heads on long necks, the pliosaurs had enormous heads on short necks, the skull alone sometimes reaching 3 meters or more in length. Kronosaurus, Pliosaurus, and the recently described Predator X from the Late Triassic of Norway were among the most formidable predators that have ever existed in the ocean. Their jaws were lined with massive conical teeth that could crush and grip the largest prey. They fed on other marine reptiles, on large fish, on sharks, on whatever they could overpower in the deep. Imagine encountering a large pliosaur in its own environment. The ocean around you is clear and warm, the light filtering down from the surface in long blue-green columns. Below, the darkness deepens into the abyss, and from that direction, from the darkness below, something is rising. It rises slowly at first, then faster. The shape becomes clear, a massive, roughly streamlined body, the 4 flippers generating a smooth, powerful undulation as it rises. The head, the enormous head, 1.5 meters, 2 meters wide. The jaws, the teeth visible even from this distance. You would have no time for the contemplation we are indulging in, but we have the luxury of watching from a distance, from the safety of imagination, and from that distance the rising pliosaur is magnificent. A thing of terrible, absolute biological purpose. 100 million years of ocean predator evolution distilled into one perfect, lethal shape. It does not see you. You're not what it is looking for. It is looking for something large enough to be worth the effort, and it is, in its own way, beautiful. The way that all real things are beautiful when you see them clearly, without the filters of fear or preference or the need to make them mean something beyond what they are. The Mesozoic seas were full of such moments. The slow, patient cruise of an ichthyosaur in the open ocean, the ambush of a mosasaur in the shallows of the late Cretaceous inland sea, the feeding dives of a plesiosaur into a ball of fish, the constant endless cycle of predation and evasion and survival that drives all marine ecosystems as surely as it drives all terrestrial ones. Ammonites populated these seas in extraordinary diversity and numbers. Their spiral shells, from a centimetre to 2 metres in diameter, accumulated in such quantities in the Mesozoic sediments that they are now among the most common fossils in Mesozoic rocks. Living ammonites were jet-propelled, active swimmers, their coiled shells serving as buoyancy devices, and their soft bodies equipped with powerful tentacles for capturing prey. They were intelligent in the limited sense that cephalopods are intelligent, capable of rapid responses and some degree of learned behaviour, their large, complex eyes providing excellent vision in the dimly lit depths. The ecological role of ammonites in the Mesozoic seas was enormous. They were prey for virtually all the large marine predators, a critical link in the food chain between the smaller organisms they ate and the great reptilian predators that ate them. Their extinction at the end of the Cretaceous, coinciding with the extinction of the non-avian dinosaurs, removed a major component of the marine food web and contributed to the cascading effects that restructured ocean ecosystems in the early Paleocene. The end of the Mesozoic was not just an ending for the land, it was an ending for the sea as well, a transformation of the ocean that changed its ecological structure in ways that still echo in the ocean ecosystems of today. The modern ocean, with its whales and dolphins and large fish as the dominant large fauna, is in part defined by the absence of the mosasaurs and plesiosaurs and ichthyosaurs that preceded them. The niches those animals filled were refilled, in the Paleocene and Eocene and Miocene, by the marine mammals that evolved from their land-dwelling ancestors, filling the same ecological roles by completely different evolutionary paths. The ocean, like the land, was rebuilt, different, but still recognizable as an ocean, still full of life, still producing in its warm, productive shallows and its cold, dark depths, the extraordinary diversity that makes it the most species-rich environment on Earth. And somewhere in the sediments of the ocean floor, in the compressed and transformed remains of all the Mesozoic animals that sank to the bottom and were buried there across 185 million years, the record of that ancient world is preserved, waiting, in the patient way of geological things, for the curious minds that will one day find it and try to understand it. We are those curious minds, and this is what we have found, this ocean, this ancient, extraordinary, irretrievable sea. Let it wash over you now, the warm Mesozoic ocean, the clear water above and the blue depths below, the ammonites moving in their slow spiral courses, the sound of the open sea, which has not changed in 400 million years, the sound of water, the most fundamental sound in the world, the sound that surrounds the birthplace of all life. You are very far back now, very deep in time, and the water is warm and the world is ancient and everything is exactly as it was, long before there was anyone to know it or name it or remember it. Rest here. Let the ancient sea hold you. Let the deep time of the ocean be your lullaby. You're safe in the water of the world's beginning, safe in the long, patient history of life. If you are enjoying this journey, please leave a like and subscribe to the channel. It really helps us create more content like this. We are now in the final chapter of the dinosaur age. The late Cretaceous, roughly 100 million years ago to 66 million years ago, is a world that stands at the very apex of dinosaurian evolution. It is also, without knowing it, a world living on borrowed time. But let us not rush to that ending. Let us stay here a while in this extraordinary age and walk through it slowly. The western interior of North America in the late Cretaceous is one of the most intensively studied prehistoric environments in the world, and with good reason. The rocks of the Hell Creek Formation, the Judith River Formation, the Lance Formation, and their equivalents across the American West preserve an extraordinary record of late Cretaceous life, a window into the final few million years of the Dinosaur Era that is detailed enough to paint a rich picture of daily life. Imagine the Hell Creek world, approximately 68 to 66 million years ago. A broad coastal plain slopes gently toward a warm inland sea that covers much of what is today the central United States and Canada. This western interior seaway divides North America into two landmasses. To the east, an island continent called Appalachia. To the west, Laramidia, the landmass where some of the most famous dinosaurs of all time live out their days. The climate is warm and humid, subtropical in much of the region. Dense forests of palms, magnolias and conifers line the rivers and cover the higher ground. Ferns and flowering ground cover plants carpet the forest floor. Cycads and ginkgos still grow alongside the newer angiosperms. The world smells of flowers and wet earth, and the particular richness of a warm, productive landscape. And into this world we bring the most famous dinosaur of all, Tyrannosaurus rex. There is a reason this animal captures the imagination above all others. It is not simply its size, though that is extraordinary. An adult Tyrannosaurus may have been 12 to 13 meters long and weighed somewhere between 7 and 14 tons. It is not simply its teeth, though those are remarkable, serrated, banana-sized, capable of crushing bone. It is something about the combination of its features, the massive skull disproportionate to its body, the tiny forelimbs that seem almost vestigial, the enormous powerful hind limbs built for both support and locomotion. Tyrannosaurus in life would not have been the running, roaring monster of popular culture. Its enormous mass would have limited its top speed to perhaps 17 to 25 kilometers per hour, a brisk human running pace, but not the sprinting terror of the movies. It was likely more of an ambush predator in some situations, using its acute senses, particularly its keen sense of smell and its binocular vision, to locate prey before committing to an attack. And that sense of smell was extraordinary. The olfactory bulbs of Tyrannosaurus, visible in casts of its brain case, were enormous relative to the rest of its brain. It could likely detect the scent of blood or a carcass from many kilometers downwind. This suggests that, like modern large predators such as lions and crocodilians, Tyrannosaurus was probably not above scavenging when a meal presented itself without the risk of a hunt. What did its voice sound like? We genuinely do not know. The roar depicted in popular culture is almost certainly wrong. Birds, the living descendants of theropod dinosaurs, do not produce sounds by vibrating vocal folds the way mammals do. They use a completely different vocal structure. Many researchers now think that large theropods may have produced closed-mouth sounds, low-frequency vocalizations made by compressing air through a closed mouth and throat, producing deep booming or hissing sounds rather than roars. If this is correct, an encounter with a Tyrannosaurus would have been accompanied not by a Hollywood roar, but by a deep resonant boom that you would feel in your chest and your bones before you heard it with your ears. Let that settle into your imagination. The vibration before the sound, the way the air itself seems to tighten. But Tyrannosaurus does not exist in isolation. It is part of a community, and that community is rich and complex. The herbivores of the Hell Creek world are formidable. Triceratops is the most abundant large herbivore, and it is a remarkable animal in its own right. With its 3 horns, the 2 large brow horns that could be nearly a meter long in adults, and the shorter nasal horn, along with its broad frill edged with small bony projections, it is one of the most visually striking animals of the Cretaceous. An adult Triceratops weighed perhaps 8 to 12 tons, making it roughly comparable to Tyrannosaurus in mass. It was not helpless prey. Evidence of combat between Tyrannosaurus and Triceratops exists in the fossil record. Triceratops bones with Tyrannosaurus bite marks. Tyrannosaurus bones with healed injuries consistent with horn damage. These two animals knew each other. They had shaped each other's evolution. The long horns of Triceratops were not just for display, they were for this. For the moment when the shadow of a large predator fell across a grazing animal, and the choices narrowed down to fight or flee. Edmontosaurus, the large hadrosaur of the Hell Creek world, was another abundant herbivore. Some specimens have been found with a soft tissue crest on top of the head, suggesting that even without the elaborate hollow bony crests of animals like Parasaurolophus, Edmontosaurus was still making visual statements to others of its kind. It was a large animal, sometimes exceeding 13 meters in length, moving in herds through the forests and along the riverbanks. The smaller dinosaurs of this world are often overlooked in the fascination with the giants, but they were a crucial part of the ecosystem. Pachycephalosaurus, a plant-eater with a thick, domed skull, possibly used headbutting in intraspecific combat the way bighorn sheep do today. Ankylosaurus, encased in its remarkable armour, moved through the forest understory like a living tank. Small theropods like Pectinodon and the raptors of this period darted through the undergrowth and along the forest floor. And the birds. The late Cretaceous is alive with birds in the sense that many of the small feathered theropods of this time are definitionally or near definitionally birds. Confuciusornis and similar forms have long since appeared. True modern type birds, the ancestors of all living bird lineages, are present and diversifying. Some are shorebirds, wading the edges of the inland seaway. Others are forest dwellers. Others have adapted to purely terrestrial lives. They fill the air with movement and sound, these small feathered dinosaurs, in a way that would feel oddly familiar to any modern observer. A day in the Hell Creek world is long and full. The morning begins with the sounds of the forest, bird calls and insect rhythms, the distant splashing of large animals at the river. Mist rises from the floodplain as the sun warms the cool morning air. Edmontosaurus herds move out from the forest into the more open areas to feed, their heads sweeping back and forth through the vegetation, the adults watchful and the young staying close. A triceratops moves slowly through the edge of the forest, head down, cropping vegetation with its powerful beak. It is an older animal, its horns heavily worn, its frill marked by the scars of past combats. It moves with the slow certainty of an animal that has survived long enough to know when to be cautious, and when it is safe to simply eat. The afternoon builds heat. Large animals rest in whatever shade is available. The river draws them, a crossing. The broad, slow-moving river that winds through the floodplain is both resource and obstacle. Animals gather at its banks, drink, sometimes cross to the vegetation on the other side. The crossing is the most dangerous moment. The mud can be treacherous. The current is unpredictable, and in the water and on the banks crocodilians wait with a patience measured in geological time. The evening comes slowly in the late Cretaceous, the light going golden and then orange as the sun descends. The sounds of the forest change as the day animals begin to settle, and the night animals begin to stir. Small feathered theropods hunt insects in the fading light. Something large moves in the darkness at the forest edge, a shape too big to miss but too dark to identify clearly. The stars appear above the Hell Creek world, the same stars in different positions but the same fundamental sky. Light that has travelled for millions of years reaching a world that will not last much longer. We do not know that, here in the late Cretaceous. Neither do the animals. They simply live their days as they have always lived them, fully present in the only world they know, unaware that in the darkness of space, something is travelling toward them that will end everything they have ever known. But that ending has not come yet. Not tonight. Tonight the Hell Creek world is alive and full, and breathing under its ancient stars, and the darkness is soft and warm, and somewhere in the distance Tyrannosaurus is following a scent trail through the night forest, moving with a slow, heavy deliberateness that is almost meditative, each footfall measured, each breath deep, alive in its enormous body in the last great age of the dinosaurs. Let the image of that night settle over you, the warm air, the soft sounds of a sleeping world, the ancient stars above. You are resting now, deeply resting, and the world around you is ancient and alive and full of wonders you are only beginning to understand. The late Cretaceous world was also a world of rapid change in ways the animals themselves could not perceive. The continents had by now moved to positions not very different from those they occupy today. India was moving northward on a collision course with Asia that would one day throw up the Himalayas. Antarctica was drifting toward the pole. Australia was separating from Antarctica. The geography of the world was becoming recognizable to modern eyes, even if the climate and the life remained profoundly alien. Marine life had reached its own pinnacle of diversity and complexity. The great inland seas were full of mosasaurs, enormous marine lizards that had evolved from land-dwelling relatives and now dominated the ocean's top predator niches, in the absence of the ichthyosaurs and plesiosaurs that had preceded them. Sharks of modern-looking forms patrolled the depths. Sea turtles of tremendous size navigated the warm, shallow waters. Ammonites, those spiral-shelled relatives of nautiluses, filled the seas in extraordinary diversity, their coiled shells accumulating in such quantities that their fossils became among the most common and widespread in the Cretaceous rock record. The sky over the late Cretaceous oceans was full of the largest pterosaurs, and now, increasingly, it was also full of birds. Modern bird lineages, the ancestors of ducks and shorebirds and other water birds, were already present by the end of the Cretaceous, finding their niches along the coasts and inland waterways. The age of birds was already beginning before the age of dinosaurs had even ended. The two ages would overlap. They would blend. Because of course, birds are dinosaurs, they always were. The line between the feathered theropods of the Cretaceous and the birds that fill our modern skies is unbroken. Life does not end cleanly, it transforms. But transformation, when it comes, often comes through catastrophe, and the catastrophe that is coming toward the Cretaceous world is the most dramatic in the history of complex life since the Great Dying. The world of the late Cretaceous was more dynamic, more changeable than the image of a stable, dinosaur-dominated world might suggest. Sea levels were fluctuating. Volcanic activity in various parts of the world was releasing gases that affected the climate. The continents were continuing their slow dance of separation and collision. Species were evolving, migrating, going extinct locally, adapting to slowly shifting conditions. In what is now India, a massive volcanic event was underway that would, in another context, have been catastrophic. The Deccan Traps, a flood basalt province roughly comparable in scale to the Siberian traps that had caused the Great Dying, were erupting. For hundreds of thousands of years before the asteroid impact and for hundreds of thousands of years afterward, the Deccan Traps poured lava across the Indian subcontinent in pulses, releasing carbon dioxide and sulfur dioxide into the atmosphere in quantities large enough to affect the climate significantly. Some researchers have argued that the Deccan Traps were already causing significant ecological stress in the late Cretaceous before the asteroid impact, and that the biosphere was therefore in a weakened state when the impact occurred. Others argue that the asteroid impact was so overwhelming in its effects that the prior condition of the biosphere was largely irrelevant. The truth is probably somewhere in between, and the details are still being actively debated. What is clear is that the late Cretaceous was not a static world blissfully unaware of its impending end. It was a world already experiencing change, already adapting to shifting conditions, already losing some species and gaining others as the long, slow processes of geological change reshaped the environment. The asteroid impact was the final, overwhelming blow to a world that was already, in some ways, under stress. But even stressed worlds are full of life. Even in the last million years of the Cretaceous, as the Deccan eruptions were beginning, and the sea levels were fluctuating and the species compositions of many ecosystems were shifting, the dinosaurs were still there. Still breeding, still migrating, still establishing territories, still nursing their young, still doing all the things that living animals do in their living world. A Tyrannosaurus in the late Cretaceous did not know it was living at the end of an age. It knew the smell of its territory. It knew the location of the best hunting grounds. It knew the individual scents of the animals it competed with. It knew perhaps the presence of its own offspring, those enormous juveniles that looked so different from itself yet carried its genes forward. It lived in the immediate present of its own experience, as all animals do, fully absorbed in the texture of its own existence. There is something both humbling and comforting in this, the immediacy of animal life, the absolute absorption in the present moment that non-human animals appear to experience, untroubled by the knowledge of their own mortality, unaware of the geological context of their existence. A Tyrannosaurus was, in this sense, completely free of the awareness that is both our greatest gift and our heaviest burden. The ceratopsians of the very end of the Cretaceous were among the most spectacular animals that have ever lived. Triceratops, the most familiar, is also one of the most thoroughly studied, with hundreds of specimens known from the Hell Creek Formation. Analysis of Triceratops' growth series, juveniles to subadults to mature adults, shows that the skull changed dramatically with age. Young Triceratops had relatively short horns and small frills. As the animal matured, the horns lengthened and curved, the frill expanded and developed more elaborate bony projections at its margin. The adult skull, massive and elaborately ornamented, was the product of years of growth and represented a clear signal of age and therefore presumably experience and dominance. There is also evidence of individual variation in Triceratops, differences in horn length and curvature and frill shape that were probably unique to each individual, and that may have allowed other Triceratops to recognize each other as individuals. If this is so, then the social lives of Triceratops were more complex than we might assume, involving not just the recognition of species and sex, but the recognition of specific individuals, the foundation of the kind of social memory that is associated with complex social behavior in modern animals. We will never know the full complexity of Triceratops' social life, but the bones hint at it, and the hints are tantalizing. Near the very end of the Cretaceous, the Hell Creek world was changing. Sea levels were dropping as the global climate slowly shifted. The inland seaway that had divided North America for most of the late Cretaceous was retreating, exposing new land areas that new populations of dinosaurs were beginning to colonize. The vegetation was changing as different temperature and precipitation patterns reorganized the plant communities. The diversity of some dinosaur groups appears to have been declining slightly in the very latest Cretaceous, though this interpretation is debated. But Tyrannosaurus and Triceratops were still there, right up to the end, as far as the fossil record can tell us. Their fossils are found within the very topmost layers of the Hell Creek Formation, the layers that directly underlie the thin dark band of iridium-enriched clay that marks the impact. They were alive when it happened. They were part of the world that ended. The sky over the Hell Creek world on the last normal night would have been the same sky as any other night. The stars, the constellations in positions somewhat different from their modern locations, because the Earth has moved through the galaxy in the intervening 66 million years. The sounds of the night fauna, the slow, regular breathing of sleeping animals, the distant splash of something in the river, the calls of nocturnal birds. No different from any other night, except that it was the last. And we cannot know this, lying in the darkness with the stars above us. We can only know it afterward, looking back. In the moment, the last night of an age feels like every other night. This is the peculiar mercy that the present always extends to us. The present is always just the present, never its own ending. We tend to imagine the dinosaur world as a daylight world, the great animals moving through a sun-drenched landscape in the full heat of the Jurassic or Cretaceous afternoon. But the night has always been half of every world, and the dinosaurs inhabited the night as fully as they inhabited the day. The evidence for nocturnality in some dinosaur species comes from the structure of their eyes, specifically from the size of the sclerotic rings, the ring of small bones that support the eyeball in birds, reptiles, and many non-mammalian vertebrates. Large sclerotic rings relative to the overall size of the eye indicate large eyes, with wide pupils capable of gathering more light, the same adaptation seen in modern nocturnal animals. Some small theropods, particularly the troodontids, had disproportionately large eyes with sclerotic ring proportions suggesting strong nocturnal capabilities. This makes ecological sense. The mammals that shared the Mesozoic world with the dinosaurs were mostly small and nocturnal, having been pushed into the nighttime niche by competitive pressure from the diurnal dinosaurs. If some theropods evolved the ability to hunt efficiently in the dark, they could have exploited this resource of nocturnal mammals that the daytime predators could not reach. The picture that emerges is of a dinosaur world divided across time as well as space, with different species active at different times of day and night, reducing competition and allowing more species to coexist than would be possible if all were restricted to the same temporal niche. This temporal partitioning is a feature of all complex ecosystems, and the dinosaur world was no exception. The Jurassic and Cretaceous nights would have been alive with activity. Small theropods and early birds hunting insects in the dusk and dawn. Larger animals moving through the darkness with the confidence of animals that know their territory. The small mammals emerging from their burrows as the sun went down, darting between the legs of any sleeping giants, exploiting the insect life that the darkness brought out. The sounds of the Mesozoic night would have been extraordinary. Insects, always the dominant sound producers of warm climate nights, providing the constant background. The calls of whatever nocturnal dinosaurs were active. The movement of large animals audible even in the dark. The ground vibrating faintly with each footfall of a passing sauropod. The distant splash of something entering or leaving the river. And above it all, the stars. The same stars in their slowly precessing positions that we see today. The Milky Way visible with a clarity impossible in our light-polluted world. The slow movements of the planets across the dark sky. Meteor trails now and then, a small debris from the solar system burned up in the atmosphere. A small feathered theropod resting in the branches of a Jurassic conifer, looking up at that sky, would have seen the same fundamental sky that you see when you go somewhere dark enough to see properly. The same Milky Way, the same dazzling density of stars, different constellations because the stars have moved relative to each other in the intervening 150 million years, but the same sky, the same darkness, the same ancient light. You share that sky. The most distant connection, the most improbable thread of continuity but real. The starlight that fell on a sleeping Jurassic world is still falling. It is falling now on you, filtered through the millennia but unchanged in its fundamental nature. Light from suns so far away that they were already old when the dinosaurs were young. Look up when you can. Let the sky be as old as it is. Let the stars be as far away as they are. Let the darkness between them be as deep and as full of time as it truly is. And in that depth, in that ancient light, feel the small, warm, alive fact of your own presence, here, now, breathing under this same endless sky. The dinosaurs watched it too. They did not know what it was or how far away it was or what it meant. They simply lived beneath it, as we live beneath it, small and temporary and completely, fully alive. That is enough. That has always been enough. The western interior seaway that divided North America throughout much of the late Cretaceous was not just a geographic feature. It was an ecosystem, a vast, shallow, warm inland sea that connected the Arctic Ocean to the Gulf of Mexico, dividing the continent into two separate landmasses and creating one of the most productive marine environments in the history of the Cretaceous. Imagine standing at the shore of this sea in the late Cretaceous, approximately 75 million years ago. The water is warm, much warmer than the Atlantic is today, heated by a climate that lacks the polar ice caps that currently moderate global temperatures. The shore is a broad expanse of tidal flat, the sediment dark and rich, cut by the channels of rivers coming down from the highlands to the west. Behind you, the forests of Laramidia begin, the great coastal plain where Tyrannosaurus and Triceratops live out their days. Ahead of you, the sea stretches to the horizon, its surface slightly hazy in the warm air. The water is full of life. Ammonites of every size drift and swim through the warm shallows, their spiral shells ranging from the size of a thumbnail to the diameter of a tire. Fish school in the bright surface waters, pursued from below by mosasaurs and from above by pterosaurs and early birds. The surface itself is broken occasionally by the sinuous forms of long-necked elasmosaurids, plesiosaurs that surface to breathe before diving again to pursue fish in the midwater. The mosasaurs are the apex predators of this inland sea. These are not small animals. Tylosaurus, one of the largest, reached lengths of 10 to 13 meters, comparable to a large saltwater crocodile, but moving through the water with a sinuous efficiency that crocodilians cannot match. Mosasaurs were closely related to modern monitor lizards and snakes, and their swimming motion, powered by a long flattened tail, was more snake-like than fish-like. They were fast, capable of rapid acceleration when pursuing prey, and their jaws were equipped with sharp conical teeth ideal for gripping fish and ammonites. A large Tylosaurus cruising through the middle depths of the inland sea was the ecological equivalent of a great white shark, a top predator that controlled prey populations by its mere presence, its territory marked by the wakes it left and the prey it removed from the food chain. At its size, little else in the sea could threaten it. It was the master of its environment in the way that only the largest predators can be, moving through a world that had been shaped, in part, by its own evolutionary lineage over millions of years. The birds that fished the margins of the inland sea were already diverse by the late Cretaceous. Hesperornis was a large, flightless diving bird, its wings reduced to tiny vestiges, its legs set far back on its body for efficient underwater propulsion, its jaws still equipped with teeth that no modern bird retains. It was an extraordinary animal, thoroughly adapted to its aquatic lifestyle, as different from a modern loon as a modern loon is from a sparrow, but filling essentially the same ecological role, diving for fish in the cold, productive waters. Isthyornis, by contrast, was a capable flyer, its large keel bone providing attachment for powerful flight muscles, its wings broad and efficient for soaring over the open water. It had teeth, like Hesperornis, but otherwise would not have looked dramatically out of place among modern seabirds. It was a tern-like or gull-like animal in ecological terms, swooping to the surface to snatch fish, perhaps diving briefly from the air, filling the aerial predator niche above the inland sea in a way comparable to modern seabirds above the modern ocean. The inland sea was a temporary thing, as all geographic features are temporary in geological terms. By the very end of the Cretaceous, sea levels were dropping, and the seaway was beginning to drain. By the beginning of the Paleocene, it was largely gone, and North America was reunited into a single continent. The extraordinary marine ecosystem it had supported disappeared with it, replaced by the terrestrial ecosystems that would eventually produce the Great Plains and the Mississippi River Valley and all the other familiar features of the modern North American interior. But while it lasted, it was one of the most productive and diverse marine environments in the history of the Cretaceous world. Its fossils, preserved in the chalk beds and dark shales of Kansas and South Dakota and Colorado, are among the most spectacular in North America. Entire mosasaur skeletons and perfect ammonite specimens, and the bones of Hesperornis preserved in such detail that the traces of their original soft tissue can sometimes be discerned. They are there in the rock, these ancient sea creatures, sleeping in the chalk with the patience of geological time, waiting for the curious minds that will find them and wonder about them and try to reconstruct, from their silent bones, something of the extraordinary world they inhabited. We have been reconstructing that world tonight, and it has been, for a few hours, as real as any world can be. The warm inland sea, the ammonites drifting in the shallows, the mosasaurs hunting in the depths, the pterosaurs crossing the wide sky above the water. All of it real, all of it gone, all of it present in the rock and in the mind. We have walked through time from the early Triassic to the final days of the Cretaceous, following the broad sweep of the dinosaur story. Now, let us slow down. Let us stop the clock and spend some time not in the sweep of geological time, but in the ordinary hours of ordinary days. Let us ask not what happened across millions of years, but what it was like to simply be a dinosaur on a Tuesday afternoon. This is not a question paleontology can fully answer. Behaviour leaves only indirect traces in the fossil record. We know what animals ate from their teeth and from gut contents and coprolites. We know something about how they move from trackways and bone structure. We know something about social behaviour from bone beds and nesting sites. But the texture of daily life, the moments between the dramatic, the long hours of feeding and resting and simply being alive, those we must reconstruct with care and imagination, guided by what we know. Begin with sleep. Dinosaurs slept. All animals sleep, and the fossil record offers one extraordinary glimpse of what dinosaurian sleep may have looked like. A fossil of Mei Long, a small troodontid dinosaur from China, was preserved in a sleeping posture remarkably similar to that of modern birds, its head tucked back under one arm, its legs folded close to its body. The posture is so bird-like, so immediately recognizable, that the image is almost moving in its familiarity. 125 million years ago, a small feathered dinosaur tucked its head under its arm and went to sleep. And that is the last thing it ever did. We can imagine the sleep of larger dinosaurs too. A large sauropod would not have been able to tuck its neck under anything, but it may have rested lying down, though some researchers have suggested that animals as massive as the largest sauropods may have been unable to rise from a fully recumbent position, and so slept standing, their enormous weight distributed across 4 legs. A large hadrosaur may have lain along the riverbank in the warmth of the afternoon, its sides rising and falling slowly, its eyes closed, the herd around it providing the security of numbers that allows prey animals to rest. What did they dream? This is the most unanswerable question. Modern birds dream, their brains cycling through rapid eye movement sleep states similar in many ways to those of mammals. It is likely that the theropod dinosaurs, the most bird-like in their brain structure, also experienced something like the rapid eye movement cycles that we associate with dreaming. What images moved through the sleeping mind of a velociraptor? What landscapes formed and dissolved behind the closed eyes of a sleeping hadrosaur? We cannot know, but we can imagine, and imagining it makes them feel closer to us, these ancient animals, these lives so different from ours and yet built from the same fundamental biology. Let your own eyes close a little more. Let your breathing slow. You're almost dreaming yourself now, and somewhere in that space between waking and sleep, the dinosaurs are there too, resting in their ancient world, and for a moment the distance of 66 million years collapses to nothing. Young dinosaurs grew fast. This is one of the most important discoveries of modern paleontology, transforming our understanding of dinosaur biology from cold-blooded, reptile-like slowness to something much more dynamic. By examining the bone structure of dinosaur fossils under microscopes, paleontologists have discovered growth rings in the bone tissue similar to tree rings, and the spacing of those rings reveals growth rates that were rapid, sometimes extraordinarily so. A Tyrannosaurus, for example, did not reach its enormous adult size through slow, cold-blooded growth over decades. It grew rapidly through its teenage years, putting on as much as 2 kilograms per day during its peak growth phase. This rate of growth is more comparable to a warm-blooded bird or mammal than to a cold-blooded reptile. By around 20 years of age, most Tyrannosaurus individuals had reached or approached their adult size. The maximum documented age in the fossil record is around 30 years, though some individuals may have lived longer. This rapid growth has implications for what young Tyrannosaurus individuals were like. A 5-year-old Tyrannosaurus was not a tiny version of the adult. It was a completely different ecological player. Smaller, faster, more lightly built, with a different skull shape and different teeth. It was essentially filling a different niche from its parents. Some researchers have proposed that juvenile tyrannosaurids may have been fast pursuit predators, filling the niche left open by the absence of other medium-sized theropods in late Cretaceous North America, while the adults became the slow, crushing ambush specialist that the fossil record depicts. Think about what this means for family life, for the dynamics within a dinosaur community. A juvenile Tyrannosaurus encountering a fully grown adult was not encountering an older version of itself. It was encountering something so much larger and more powerful that the relationship between them was more analogous to the relationship between a house cat and a lion than between parent and child. Did Tyrannosaurus parents care for their young? This we genuinely do not know. Modern crocodilians, the living reptiles most closely related to dinosaurs and pterosaurs in terms of overall body plan, do show parental care, guarding nests, and sometimes carrying young in their jaws. Many modern birds, of course, are famous for their elaborate parental care, the most intensive in the animal kingdom. It seems reasonable to assume that many dinosaurs showed some degree of parental investment beyond simply laying eggs, but the evidence is limited. Nesting sites have been found for a number of dinosaur species, and some of them are remarkable. Maiasaura, a hadrosaur from the late Cretaceous of Montana, whose name literally means good mother lizard, was found in a nesting ground with evidence of communal nesting, adult animals associated with nest sites, and bone evidence suggesting that juveniles remained in or near the nest for some time after hatching, their leg bones not yet fully ossified, and therefore not capable of supporting sustained locomotion. This implies that adult Maiasaura were bringing food to their young, tending the nest, and protecting the young animals in a way that required sustained parental attention over weeks or months. This is not the cold-blooded reptile of old depictions. This is an animal with something that looks very much like the warmth of a parent. Consider the day of a Maiasaura in the late Cretaceous nesting ground. The colony is large, dozens of nests spread across a hillside or flat area, the mound-shaped nests made of vegetation and soil. The summer is warm and the vegetation is lush, and the adults must balance the competing demands of feeding themselves and tending their nests. A female returns to her nest in the late afternoon, having spent the morning feeding in the valley below. She approaches her nest slowly, recognizing it by scent and position, and settles beside it. The young inside, still small and downy, raise their heads at her approach, their mouths opening with the universal language of hungry young animals. She brings vegetation. She tears it into smaller pieces and places it within reach of the young. They feed with the eager, slightly clumsy energy of animals that have not yet fully coordinated their bodies. She watches over them, alert to any disturbance in the colony, any sign of a predator drawn by the smell of so many young animals concentrated in one place. This is not so different from the scene at a modern colony of ground-nesting birds. The fundamentals of parental care seem to have been established very early in the dinosaur lineage, perhaps even before the first true birds. It is one of the threads that connects us to them, these ancient animals, across the vast distance of time. The social lives of dinosaurs were complex in ways we are only beginning to understand. Trackways, those fossilized footprints preserved in ancient muds and sands, sometimes show multiple individuals of the same species moving together, Their tracks parallel, suggesting coordinated movement that implies social bonds. Bone beds, accumulations of bones from multiple individuals of the same species, sometimes reveal mass deaths from catastrophic events like floods, and they tell us that these animals were gathered together in groups large enough to die together. Ceratopsians, the horned dinosaurs, appear to have been strongly gregarious. Enormous bone beds of Centrosaurus and other ceratopsians in Canada suggest that these animals moved in herds of sometimes hundreds of individuals, following seasonal migrations in search of food and water, in a way analogous to the great ungulate migrations of the modern African savanna. Imagine that, a Cretaceous version of the wildebeest migration, hundreds of horned dinosaurs moving across the landscape in a vast, slow-moving column, their footfalls making the ground tremble, the dust rising in a visible cloud above them, the calls of adults and young mixing into a continuous resonant sound that carries for kilometers in every direction. Predators following the margins of the herd, watching for weakness, waiting for the opportunity. The great cycle of predator and prey enacted at a scale that is almost beyond imagining. And at the end of such a day, as the herd settles for the night, the sound gradually diminishes. The calls grow less frequent, the movement slows, the enormous animals lie down or stand in the darkness, and the stars come out above the Cretaceous plain, and the world grows quiet in the way that only truly wild places can grow quiet, with a quality of silence that is full rather than empty, full of the breathing of many animals, the distant calls of nocturnal hunters, the rustle of small things in the grass. You are part of that quiet now. You have settled into the rhythm of this ancient world, this world of extraordinary life lived at every scale, from the smallest insect in the ferns to the greatest sauropod striding the floodplain. Your own breathing has slowed to match the rhythm of the darkness. The dinosaurs are resting, and so are you. There is one more aspect of the dinosaur world we should explore before we move toward the ending of their age, and that is the question of beauty. Not our beauty, the human sense of aesthetics that arose in a completely different evolutionary context, but something in the dinosaurs themselves. Because it seems, increasingly, that many dinosaurs were beautiful in ways that were meaningful to them. The elaborate crests of the hadrosaurs, the magnificent frills and horns of the ceratopsians, the iridescent or brightly coloured plumage that some feathered theropods almost certainly possessed, based on what we know about the evolution of feather coloration, the display structures and vocalizations and behaviours that all of this ornamentation was in service of. Beauty, in the biological sense, is communication. It is the signal that says I am healthy, I am fit, I am worth attending to. And for that signal to work, the receiver must be able to perceive it, must have senses calibrated to see and hear and respond to what is being displayed. The elaborate ornamentation of the dinosaurs implies that there were dinosaur eyes calibrated to see it, dinosaur brains capable of evaluating it, dinosaur psychology that responded to it with something that, if not identical to what we call attraction or admiration, was at least functionally analogous. The late Cretaceous world was not just a world of survival and predation. It was a world of display and recognition, and the ancient wordless conversation between individuals of the same species. A world of colours and sounds and the elaborate performances of animals communicating across the gaps between individual lives. That too is part of the dinosaur story. That too is what we're saying goodbye to when we approach the end of their age. The question of intelligence in dinosaurs is one that science is still wrestling with, and the answers are becoming more interesting as our understanding deepens. For much of the 20th century, dinosaurs were portrayed as dim-witted animals, their small brains relative to body size taken as evidence of limited cognitive capacity. But this assessment was based on an oversimplification that more recent work has complicated considerably. Brain size relative to body size, measured as the encephalization quotient, does correlate broadly with behavioral complexity in living animals. But the relationship is not simple, and the use of fossil endocasts, the casts of the brain cavities preserved in some dinosaur skulls, to infer cognitive capacity is limited by many factors. We can measure the size of the brain cavity, but we cannot directly observe the organization of the brain tissue within it, and it is the organization, the relative development of different brain regions that most directly relates to cognitive capacity. What we can say is that the theropod dinosaurs, and particularly the Maniraptorans, The group that includes the raptors, the oviraptorids, and the birds had brain-to-body ratios comparable to those of modern crocodilians at the lower end and modern birds at the upper end. The larger-brained Maniraptorans, those with encephalization quotients approaching those of modern crows or parrots, were almost certainly capable of complex behaviors, including learning, social recognition, and possibly even simple problem-solving. The corvids, the family of birds that includes crows, ravens, jays, and magpies, are today recognized as among the most cognitively complex animals on Earth, capable of making and using tools, solving multi-step problems, planning for the future, understanding the perspectives of other individuals, and even demonstrating what appears to be a rudimentary theory of mind. And corvids are dinosaurs. Their cognitive abilities did not appear from nowhere in the Cenozoic. They are the product of the long trajectory of theropod brain evolution that began in the Triassic and reached its current expression in the modern birds. The Troodontids, a group of small Maniraptoran theropods from the Cretaceous, had some of the largest brains relative to body size of any non-avian dinosaur known. Troodon, the most famous member of the group, has sometimes been used in speculative discussions of what might have happened if the non-avian dinosaurs had survived the asteroid impact. Would they have eventually evolved human-like intelligence? It is a seductive thought experiment, even if it is ultimately unanswerable. But the fact that it is even worth asking says something about the cognitive trajectory that some dinosaur lineages were on. The social behaviors of dinosaurs, where they can be inferred from the fossil and trace fossil record, suggest cognitive complexity consistent with their brain sizes. The herding behavior of ceratopsians and hadrosaurs, evidenced by the bone beds, implies the ability to maintain social cohesion in large groups, to recognize other individuals, to navigate the complex social hierarchies that large group living always involves. The parental care evidenced by nesting sites implies the ability to form attachments, to recognize and respond to the needs of offspring, to maintain behavior patterns oriented toward a future state, rather than purely toward immediate reward. None of this is as sophisticated as human cognition. None of it approaches the recursive, language-mediated, self-aware intelligence that is our particular specialization, but it is far from the empty, mechanical behavior of a simple reflex animal. The dinosaurs were thinking creatures, in whatever sense that word can be applied to animals that lack language. They experienced the world through senses and processed that experience through brains capable of learning, social recognition, and appropriate behavioral flexibility. They were, in other words, alive in all the ways that matter. The experience of a young dinosaur must have been rich with learning, a juvenile triceratops learning to navigate the social hierarchy of its herd, a young velociraptor learning from its parents or from trial and error the techniques of hunting, the timing of the strike, the angle of approach, the reading of prey behavior that is the difference between a successful hunt and a missed opportunity. A juvenile Maiasaura learning the migratory routes and the location of food and water sources and the individuals in its herd who could be trusted and the dangers to be avoided. All of this learning implies memory. Memory implies a kind of inner life, a record of experience that influences future behavior. And a record of experience is, in its most basic form, a kind of self. Not the self-aware, linguistically mediated self of human consciousness, but something simpler and more immediate. A body that remembers, a brain that has been shaped by its history. We are not so different in the end. We are more complex, more self-aware, more capable of reflecting on our own experience. But we share with the dinosaurs the most fundamental of all biological facts. We are alive, we experience our world, we remember, and we act on what we remember. The gap between their experience and ours is large, but it is not infinite. It is a difference of degree rather than kind. This is one of the most profound things that the study of dinosaurs can teach us if we let it. That consciousness, in its many forms and gradations, is not a uniquely human achievement, but a feature of life itself, present in varying degrees in every animal that has ever lived. That the world has always been full of experiencing beings, animals feeling the warmth of the sun and the sharpness of hunger and the satisfaction of a successful hunt, from the first nervous systems in the Cambrian seas to the last Tyrannosaurus in the Hell Creek forest. We are not alone in having an inner life. We never have been. The universe has been full of inner lives since long before we arrived to wonder about it. Let that settle around you, the fullness of the world, the extraordinary richness of experiencing beings, past and present, each one alive in its own way, each one carrying its own small portion of what it means to be alive. You are one of them. You have always been one of them. And in the darkness and the quiet and the slow rhythm of your own breathing, you're connected to all the others, across all the ages, in the only way that truly matters. You are here, you are breathing, you are alive. We have come a long way tonight, from the recovering world of the early Triassic, through the long centuries of the Jurassic and Cretaceous, through the catastrophe of the end and the quiet recovery that followed, and all the way to the present, where the birds carry the lineage forward in the morning sky. The dinosaur story is the longest story of success in the history of complex land life. 180 million years. For perspective, consider that the first anatomically modern humans appeared only 300,000 years ago, that the entirety of recorded human history spans only about 5,000 years. The dinosaurs were here for 36,000 times as long as the entirety of recorded human civilization. They inhabited and were shaped by a world that existed on a timescale we cannot intuitively grasp, only intellectually. And yet here we are, having grasped it, or having tried to grasp it, across the course of this night. We have walked in imagination through worlds so different from ours that they might as well be other planets, and we have found them full of familiar things, hunger and rest, predator and prey, parent and young, the warmth of the sun and the coolness of water, and the particular quality of silence that comes at the end of a day. These are the things that do not change, regardless of which age they inhabit. The fundamentals of being alive are the same for a triceratops and a human being, at some level below the complexity of language and culture and self-awareness that separates us. We are both alive, we both breathe, we both need to eat and rest and find safety and connection. We are both temporary, we are both part of the same long story. The fossil record does not lie. The bones in the rock are the bones of real animals that once moved and breathed and ate and slept and died. The footprints in the ancient mud are the footprints of real creatures going about their real lives. The nests with their preserved eggs are the real nests of real mothers who cared, in their own way, for the lives they were bringing into the world. Knowing this, really knowing it, changes something. It makes the world larger and older and stranger and more precious. It makes the ordinary miracle of being alive feel more extraordinary. It makes the morning sky, full of birds that are living dinosaurs, feel like a gift from a world so ancient we can barely comprehend it. That's the gift of the dinosaur story if we receive it properly, not just knowledge, not just the satisfaction of understanding something complex, but a deep felt connection to the long history of life on this planet, a sense of belonging to something enormous and ancient and resilient and beautiful. You belong to it. You have always belonged to it, and tonight, having travelled through the ages together, you feel it a little more clearly than you did before. Take that feeling with you into sleep. Let it be the last thing your waking mind holds. The ancient world full of extraordinary life, the long story still going, the morning birds already preparing their songs for the day that is coming. You are part of all of it. You are carried by all of it. You're safe in the oldest story there is. Good night. Sleep well. The world is ancient and full of wonders, and it will still be here when you wake. You have travelled far tonight, across oceans of time, through worlds of fire and green and ice and warmth, through the long, patient centuries of the dinosaur age, through its ending, through the quiet that followed. Now let the journey slow. Let the images soften at their edges. Let the ancient landscapes dissolve gently, the way dreams dissolve when you try to hold them too tightly, leaving only a warmth behind, a sense of something vast and old and kind. The Triassic is behind you. The red sand and the dry heat and the small, quick shapes of the first dinosaurs moving through the early evening. All of it behind you now, settling into the distance of deep time. The Jurassic is behind you. The enormous sauropods in the golden afternoon light, the river and the forest and the warm, rich smell of a world in its fullest expression. Behind you, settling, becoming part of the deep past. The Cretaceous is behind you. The hadrosaurs calling across the floodplain, the ceratopsian herds moving in their thousands, the great heavy presence of Tyrannosaurus in the night forest, the asteroid crossing the sky, all of it behind you now, passing back into the stone from which it came. And you are here, in the present, in the warmth of your own resting body, in the quiet dark of your own space. The world outside is the world it has always been, full of the descendants of survivors, full of living things doing what living things do, going about the extraordinary ordinary business of being alive. You have brought something back from the journey, a sense of scale, a sense of resilience, a sense of belonging to something ancient and vast and continuous. These things are yours now. They came with you out of the deep time, and they will still be with you when you wake. For now, though, rest. Let the breathing slow. Let the thoughts become less distinct. Let the images blur into the warm, formless space of approaching sleep. The dinosaurs have walked you here across 180 million years, and now they step back, these ancient and extraordinary animals, into the deep time where they live, where they have always lived, where they will always live as long as there are curious minds willing to go looking for them in the rock. Sleep well. The morning is coming, the birds will sing, the world is ancient and alive and yours. And now it is time to rest. The ancient world has held you gently tonight through every age of its long history, from the red sands of the Triassic to the lush canopies of the Jurassic, from the calling floodplains of the Cretaceous to the quiet recovery of the Paleocene dawn. Each era with its own character, its own particular quality of light and sound and life, each one gone now into the patient keeping of the rock, but here tonight, in this story, alive once more for the hours we have travelled through it together. Let the eras pass through you one last time as you drift towards sleep. The Triassic, warm and red and full of promise. The Jurassic, green and vast and loud with the movements of giants. The Cretaceous, at its peak of diversity and colour and complexity. The ending sudden and complete. The recovery slow and quiet and full of small determined things. And here, the present, with its morning birds and its deep sky, and its extraordinary, improbable human consciousness that can reach back across all those ages and find, in the ancient bones and the preserved footprints and the chemical signatures in old rock, the evidence of worlds we were not there to see. We were not there, but we went there tonight, and the going is a gift we can give ourselves whenever the world needs expanding, whenever the present feels too small or too heavy or too much. The ancient world is always available. The deep time is always there, in the rock beneath our feet, in the birds above our heads, in the shared biology of every living thing. It is yours. It has always been yours. Sleep now and carry it with you into the morning. And so we come to rest. We have travelled a long way together tonight, from the barren, recovering world of the early Triassic, through the first small steps of the earliest dinosaurs, through the long, lush corridors of the Jurassic, through the extraordinary diversity of the Cretaceous, through the fire and darkness of the ending, and out the other side into the world that survives, the world that carries the dinosaur legacy forward into the present. It has been a long journey, but it has also been a gentle one, because the story of the dinosaurs, for all its drama, is at its heart a story about life, about persistence, about the extraordinary resilience of living things in the face of a world that is always, always changing. It is a story about how things end and how endings are never quite as final as they seem. It is a story about time, and how patient time is, and how much it can hold. You have held a great deal of time tonight. You have let it pass through you like wind through a forest, touching you but not disturbing you. You're still here, in your warm, comfortable place, your body heavy and relaxed, your mind drifting in the slow currents between waking and sleep. The dinosaurs are dreaming now, if ancient things can dream. They're dreaming in the rock and the stone, in the oil fields and the coal seams, in the fossils waiting to be found in canyon walls and desert badlands, and the bottoms of ancient seas. They are dreaming in the birds outside your window, who will sing again in the morning with voices shaped by 100 million years of practice. Let the ancient world carry you now. Let the weight of all that time, all that life, all that extraordinary, improbable, magnificent existence press you gently downward into the warmth of your bed, into the darkness behind your eyes, into the deep, quiet pool of sleep that is waiting for you. The Triassic is behind you, the Jurassic is behind you, the Cretaceous is behind you, all of it is behind you, 180 million years of dinosaurs dreaming their way back through the rock. And you are here, at the very end of that long story, lying still in the darkness, breathing slowly, already halfway gone. Let the last image be this: a single feather drifting down through the warm Cretaceous air, a small brown feather shed from some small, quick, feathered thing going about its business in the forest understory. It drifts in the light that comes through the canopy in long golden bars. It turns slowly as it falls, catching the light first on one side and then the other. It is weightless and perfect and utterly without urgency. It falls. And falls. And you are falling too gently into sleep. Good night, sleep well, the ancient world is dreaming with you. Thank you so much for watching. If you enjoyed this journey through the Age of Dinosaurs, please consider leaving a like and subscribing to the channel. It really does help us continue making more content like this. We have more prehistoric worlds to explore together, more ancient stories to tell, more nights exactly like this one. Anyways, see you in the next one.